On August 12, 2024, at 3:47 a.m. Eastern Time, the James Webb Space Telescope transmitted data that would make scientists question everything we thought we knew about human history. Deep in the constellation of Virgo, on a planet designated K2-18b, Webb's infrared sensors detected something that should be impossible: molecular signatures and structural patterns that mirror technologies humans wouldn't invent for another 1,000 years. But here's where it gets truly unsettling. The light carrying this information left that planet in the year 1024 AD, while medieval knights fought in Europe and the Song dynasty flourished in China. Something on K2-18b was creating patterns that look eerily similar to what humans would eventually build, almost as if someone, or something, was following the exact same technological path we would take centuries later. The discovery sent shockwaves through NASA's Goddard Space Flight Center. Dr. Niku Madhusudan, the Cambridge astrophysicist leading the analysis, found himself staring at spectroscopic data that defied explanation. Among the expected signatures of hydrogen and helium, Webb detected something unprecedented: dimethyl sulfide, a molecule that on Earth is produced almost exclusively by life. But it wasn't just the presence of this biosignature, it was the concentration patterns, the distribution, and the accompanying chemical fingerprints that suggested something far more profound. The data revealed geometric structures in the atmospheric composition, repeating patterns in gas, distribution that shouldn't exist in nature, symmetrical formations, mathematical precision, ratios that echoed the golden ratio, Fibonacci sequences, and other signatures of deliberate design. Before we dive into this extraordinary discovery that's dividing the scientific community, hit that subscribe button right now, because what you're about to learn might fundamentally change how you think about human origins, cosmic coincidences, and whether we're truly alone in following this path of evolution. Click subscribe. This story gets more incredible with every revelation. Tonight, as you drift toward sleep, I'll guide you through the evidence that's emerged from one of the most sophisticated instruments ever created. We'll explore the possibility that what Webb found isn't just alien life, but something that mirrors humanity so precisely it raises an unsettling question. Are we following a cosmic blueprint? Did someone leave a message in the stars 1,000 years before we'd have the technology to read it? Settle in, close your eyes, and let me take you on a journey to a world 120 light-years away, where the impossible might have already happened. The James Webb Space Telescope orbits our Sun at a point called L2, a gravitationally stable location nearly 1,000,000 miles from Earth. In the profound silence of space, its golden mirrors, each precisely aligned to capture photons that have traveled across cosmic distances, peer into the atmospheres of distant worlds with unprecedented clarity. Shintusintuined, that August night in 2024, Webb's near-infrared spectrograph was trained on K2-18b, an exoplanet that had long fascinated astronomers. This world, nestled in its star's habitable zone where liquid water could exist, had been flagged as a prime candidate for detecting biosignatures, the chemical fingerprints of life. The planet itself defies easy categorization. K2-18b is neither a small rocky world like Earth nor a massive gas giant like Jupiter. Instead, it represents something we've never encountered in our own solar system: a sub-Neptune, roughly 2.6 times Earth's radius and 8.6 times its mass. Beneath its hydrogen-rich atmosphere, scientists believe an ocean might span the entire globe, a water world covered by a gaseous envelope that extends thousands of kilometers into space. As Webb's instruments dissected the starlight filtering through K2-18b's atmosphere during transit, when the planet passes in front of its host star from our perspective, the spectroscopic data began, revealing its secrets. Every molecule absorbs light at specific wavelengths, creating a unique barcode that identifies its presence. This is how astronomers can determine the chemical composition of worlds they'll never visit. The initial detections matched expectations. Hydrogen dominated the atmosphere, as predicted for a sub-Neptune. Methane appeared in significant quantities. Interesting, but not unprecedented. Water vapor signatures confirmed the planet's potential habitability. These were the results Dr. Madhusudan's team had anticipated. Then the anomalies began appearing. Dimethyl sulfide, a molecule with the chemical formula CH3SCH3, emerged from the data with unmistakable clarity. On Earth, this substance is produced primarily by phytoplankton, microscopic marine organisms that form the foundation of oceanic food chains. While some geological processes can create dimethyl sulfide in trace amounts, the concentrations Webb detected suggested biological production on a massive scale. But it wasn't just the presence of this biosignature that troubled researchers. It was the distribution pattern. When Dr. Madhusudan's team created three-dimensional maps of how gases were distributed throughout K2-18b's atmosphere, they discovered something that shouldn't exist: geometric organization. Instead of the chaotic, random distribution expected in a natural atmosphere, the dimethyl sulfide showed clustering patterns that followed mathematical principles. Picture trying to explain this to someone from medieval times, the very era when the light now reaching us first left K2-18b. Imagine describing to an 11th century scholar how molecules could arrange themselves in patterns that mirror sacred geometry, how gases could flow in currents that trace golden spirals, how atmospheric chemistry could exhibit the hallmarks of deliberate manipulation. The team ran their analysis software repeatedly, checking for instrumental errors, calibration issues, or data corruption. Every reanalysis confirmed the same impossible result. The atmospheric composition wasn't just hospitable to life. It appeared to be organized by it, structured in ways that maximized certain chemical reactions while inhibiting others. Dr. Sarah Seeger from MIT, an expert in exoplanet atmospheres, was brought in to review the findings. Her initial skepticism gradually transformed into cautious intrigue as she examined the data. What we're seeing, she explained in a hushed video conference with colleagues, resembles nothing in our models of natural atmospheric evolution. The gas distributions show signs of what we might call atmospheric engineering, deliberate manipulation of chemistry on a planetary scale. Additional analysis revealed even more puzzling characteristics. The ratios between different sulfur compounds followed mathematical sequences rarely seen in nature, but common in optimized industrial processes. The vertical distribution of gases through different atmospheric layers suggested active transport mechanisms far more efficient than natural. Convection, temperature gradients showed anomalies that couldn't be explained by stellar heating alone. Certain regions of the atmosphere maintained thermal profiles that would require energy sources beyond solar. Radiation organized energy sources that operated with remarkable efficiency. The research team faced an impossible situation. Publishing these findings would invite ridicule from some corners of the scientific community. Yet the data was too compelling to ignore. They spent months conducting additional observations, analyzing archival data from Hubble and Spitzer telescopes, and consulting with experts across multiple disciplines. What emerged was a picture of a world that challenged fundamental assumptions about how planets evolve. K2-18b's atmosphere wasn't merely inhabited, it appeared to be cultivated, maintained, perhaps even designed to support specific types of chemistry. But the true revelation came when researchers examined the temporal patterns in the data. Webb had observed K2-18b across multiple transits, building a timeline of atmospheric conditions over weeks and months. The chemical signatures showed cyclical variations, regular patterns that repeated with clockwork precision. These cycles didn't match the planet's rotation period, its orbital period, or any natural astronomical phenomenon. Instead, they operated on timescales that suggested artificial regulation. Something on or around K2-18b was maintaining atmospheric equilibrium through active processes that turned on and off according to a schedule. The implications were staggering. If these patterns represented technology, it was technology operating on a scale that dwarfed human capabilities. We manipulate our own atmosphere inadvertently through industrial emissions. Whatever shaped K2-18b's atmosphere did so with precision and purpose, maintaining chemical balances across an entire world. And all of this was happening, or had happened, while Earth's civilization struggled with iron tools and wooden ships. The light now revealing these secrets had been traveling for 120 years, meaning we were witnessing events from around 1904 by the time it reached Webb's mirrors. But K2-18b's temporal relationship with Earth created an even stranger reality. If someone on that world looked back at us with similarly powerful instruments, they would see Earth as it was around 1904, before powered flight, before radio, before any hint that an industrial civilization was emerging. The discovery forced scientists to confront an uncomfortable possibility. Perhaps technological civilization wasn't unique to humanity. Perhaps intelligence followed predictable pathways, creating similar solutions to similar problems across cosmic distances. Or perhaps something far stranger was at work, a connection between worlds that transcended simple coincidence. As news of the discovery began circulating through the astronomical community, researchers worldwide started re-examining data from other exoplanets. Were there similar patterns hiding in plain sight? Had we been missing signs of atmospheric engineering because we'd never thought to look for it? But before those questions could be answered, Webb's instruments revealed something even more unsettling: patterns in the data that looked less like natural processes and more like deliberate communication. In the sterile conference rooms of the Space Telescope Science Institute in Baltimore, a team of mathematicians, physicists, and computer scientists gathered around holographic displays showing spectroscopic data from K2-18b. What they were about to discover would transform this from an interesting exoplanet study into something that demanded explanation from fields far beyond astronomy. Dr. Elena Rodriguez, a mathematician specializing in pattern recognition and information theory, had been called in to analyze the temporal variations in K2-18b's atmospheric chemistry. Her expertise in detecting non-random patterns in apparently chaotic data made her ideal for this unprecedented analysis. What she found would keep her awake for 72 straight hours, cross-checking calculations and questioning her own sanity. The chemical cycles in K2-18b's atmosphere weren't just regular. They contained information. Using Fourier analysis and advanced signal processing techniques, Rodriguez discovered that the variations in gas concentrations, when mapped across time and wavelength, produced patterns that exhibited properties of structured data. Imagine a cosmic oscilloscope displaying the atmospheric composition of an entire world. Now, picture that display showing not random fluctuations, but waves that build upon each other, creating interference patterns, harmonics, and rhythms that contain far more organization than chance alone could produce. This is what Rodriguez saw in the data. The patterns operated on multiple nested timescales. Short-term variations cycling every 11.3 hours seemed to encode simple information, perhaps analogous to binary code or fundamental mathematical constants. Medium-term cycles spanning roughly 73 hours contained more complex structures, with relationships between different chemical species that suggested hierarchical organization. Long-term patterns emerging over weeks and months revealed the deepest structures of all. When Rodriguez applied information theoretic measures like Shannon, entropy, and Kolmogorov complexity to the atmospheric data, the results suggested a level of organization incompatible with random natural processes. The atmosphere contained what information theorists call algorithmic information, patterns that could be compressed into simpler rules, implying an underlying structure or code. But perhaps most remarkably, some of these patterns corresponded to fundamental mathematical and physical constants. The ratio between certain chemical cycles approximated p to 3 decimal places. Other relationships echoed the golden ratio, HFE for 1.618, a number that appears throughout nature and human architecture alike. Harmonic patterns in the data matched frequency ratios found in musical scales across human cultures. Dr. Frank Drake, whose famous equation estimated the number of communicating civilizations in the galaxy, was consulted about the findings. Though elderly and long retired from active research, Drake's expertise in the search for extraterrestrial intelligence made him an essential voice in evaluating these discoveries. His response was measured but significant. If this data is accurate, we're not just looking at life, we're looking at intelligence communicating through planetary-scale engineering. The team began exploring whether these patterns could represent intentional signals. One hypothesis suggested that an advanced civilization might modulate their planet's atmospheric chemistry as a form of long-distance communication, a beacon visible to any sufficiently advanced observers across interstellar distances. Unlike radio signals, which dissipate and require directional broadcasting, atmospheric signatures could be detected by anyone observing the planet through transit spectroscopy. The efficiency of such communication astounded researchers. Every time K2-18b passed in front of its star, an event occurring roughly every 33 Earth days, any civilization in the appropriate viewing angle could read the atmospheric message. The signal required no additional energy beyond maintaining the atmospheric chemistry, making it remarkably sustainable for long-term broadcasting. But the patterns contained another mystery. Some variations appeared to respond to events in K2-18b's local star system. When the host star, a red dwarf smaller and cooler than our Sun, released solar flares, the atmospheric chemistry shifted in ways that seemed coordinated rather than reactive. It was as if the atmosphere was being actively managed to compensate for stellar activity, maintaining optimal conditions despite external perturbations. Dr. Alex Chen, an expert in complex adaptive systems from Stanford, proposed a provocative interpretation. What if we're not looking at a message, he suggested, but at something more akin to planetary-scale homeostasis? Life on Earth maintains atmospheric chemistry through the Gaia hypothesis, biological processes that collectively regulate planetary conditions. What if K2-18b represents this concept taken to its logical extreme? Not just life maintaining an atmosphere, but intelligent life actively engineering it with precision? The distinction was subtle but profound. Were the patterns byproducts of sophisticated environmental management or deliberate attempts at communication? Or could they be both? Practical engineering that also served as a beacon for any observers capable of detecting it. Additional patterns emerged as the team analyzed finer details in the spectroscopic data. Certain chemical signatures showed periodic strengthening and weakening that created what scientists called spectral Morse code. Variations in absorption line depths that, while too complex to be simple binary, nevertheless exhibited clear on-off states with meaningful intervals between them. When researchers mapped these variations graphically, they discovered something extraordinary. The patterns, when visualized as two-dimensional plots, created geometric shapes, not random scatter plots or irregular distributions, but recognizable forms, circles, triangles, hexagonal structures that tessellated in ways that maximized coverage while minimizing overlap. These weren't vague resemblances that human pattern recognition psychology might impose on random data. Statistical analysis confirmed that the probability of these geometric patterns arising by chance was astronomically small, less than 1 in several trillion even with generous assumptions about natural variation. Dr. Jill Tarter, pioneering SETI researcher and former director of the Center for SETI Research, examined the data with the skepticism born of decades searching for extraterrestrial signals. Her assessment, published in a carefully worded preliminary report, acknowledged the unprecedented nature of the findings. While extraordinary claims require extraordinary evidence, and much more observation is needed, these patterns exceed the thresholds we've established for distinguishing artificial from natural signals. They exhibit characteristics we've been searching for in radio transmissions, but never thought to look for in atmospheric chemistry. The academic community found itself divided. Traditionalists argued that unknown natural processes, perhaps exotic atmospheric chemistry driven by conditions unlike anything in our solar system, could produce apparently organized patterns. We've been surprised by nature before, they argued, from pulsars initially misidentified as alien beacons to fast radio bursts that defied explanation for years. But a growing contingent of researchers found the natural explanations increasingly strained. Each new observation added complexity rather than clarity. Natural processes tend to simplify under scrutiny, revealing underlying physical mechanisms. The patterns in K2-18b's atmosphere grew more intricate and organized with every observation, suggesting the opposite. Complexity built upon complexity in ways that implied intention. The debate intensified when researchers discovered that the patterns contained what appeared to be error correction mechanisms, certain chemical signatures repeated with variations that, when analyzed through coding theory, resembled redundancy built into digital communications to protect against data corruption. It was as if the atmosphere itself was designed to maintain the integrity of information despite noise and interference. Perhaps most intriguingly, some patterns seem to reference astronomical events visible from K2-18b, when a nearby supernova exploded approximately 90 years before Webb's observations, meaning the light from that explosion would have reached K2-18b around the same time the patterns began. The atmospheric chemistry incorporated frequency ratios, matching the supernova's spectral signature. Coincidence or acknowledgement that someone on K2-18b had witnessed the same cosmic event we observed decades earlier? As the evidence accumulated, researchers faced an inescapable conclusion. Whether natural or artificial, the patterns in K2-18b's atmosphere represented something unprecedented in our exploration of exoplanets. And the most unsettling aspect was still to come. Evidence suggesting that whatever created these patterns might have anticipated our observation. Deep in the archives of atmospheric science, there exists a curious branch of research that few people outside specialized fields ever encounter. Spectral signatures of human industrial processes. Every factory, every power plant, every large-scale chemical operation leaves distinctive fingerprints in Earth's atmosphere. Unique combinations of gases in specific ratios that reveal not just the presence of industry, but its type, scale, and sophistication. When Dr. Madhusudan's team began comparing K2-18b's atmospheric patterns to this database of industrial signatures, they discovered something that would transform the investigation from abstract speculation to concrete recognition. The ratios of certain gases, the temperature profiles of specific atmospheric layers, and the energy signatures associated with chemical transformations resembled, with disturbing precision, processes that humans wouldn't perfect until the late 20th and early 21st centuries. Consider the implications carefully. The light now revealing K2-18b's atmospheric composition left that world around 1904. Yet, the chemical processes it displays mirror technologies humanity wouldn't develop for another 50 to 100 years. Carbon sequestration techniques we're still perfecting. Atmospheric filtering at scales we've only theorized. Energy distribution patterns that match our most advanced concepts for planetary engineering. Dr. Robert Zubrin, aerospace engineer and pioneer in Mars colonization concepts, was brought in to evaluate whether the observed patterns matched any theoretical frameworks for terraforming or atmospheric management. His analysis revealed startling parallels to proposals that had existed only in scientific papers and speculative engineering since the 1990s. What we're seeing, Zubrin explained in a classified briefing that was later partially declassified, resembles our own blueprints for how we would modify a planetary atmosphere if we had the resources and technology to do it efficiently. It's not just that life exists there. Something is managing that atmosphere with techniques that parallel our most advanced theoretical work. The specific technologies implied by the spectroscopic data painted a picture of remarkable sophistication. Atmospheric scrubbing mechanisms that selectively removed certain compounds while concentrating others. Gas circulation patterns suggesting active pumping or energy input at specific altitudes. Chemical gradients maintained against natural mixing that would require constant energy expenditure and precise control. One particularly striking example involved sulfur chemistry. On Earth, industrial processes often produce sulfur dioxide as a pollutant. Managing this requires sophisticated scrubbing technology that converts SO2 into less harmful compounds. K2-18b's atmosphere showed sulfur distributed in ratios that suggested not just natural biological cycling, but active chemical management remarkably similar to industrial gas treatment. The temperature inversions detected in K2-18b's upper atmosphere provided another clue. On Earth, such inversions occur naturally in our stratosphere, where ozone absorbs ultraviolet light and creates a warm layer above the cooler troposphere. But K2-18b's inversions showed patterns inconsistent with natural photochemistry alone. The temperatures varied in ways that suggested active heating from below, perhaps energy systems operating in the lower atmosphere, with waste heat rising through convection. When climate modeler Dr. Kate Marvel from NASA's Goddard Institute analyzed the thermal data, she found circulation patterns that matched computer models of optimized atmospheric management. If you were trying to maximize heat distribution across a planet while minimizing energy input, she noted, you'd create circulation cells very similar to what we're observing. It's eerily close to the most efficient designs our supercomputers produce when we ask them to optimize planetary climate control. The chemical synthesis pathways implied by the atmospheric composition revealed even more sophisticated processes. Certain organic molecules detected in trace amounts shouldn't coexist under natural conditions. They would react and break down. Their simultaneous presence suggested active synthesis, maintaining concentrations that would otherwise be chemically unstable. This paralleled advanced chemical manufacturing on Earth, where we maintain non-equilibrium conditions through continuous energy input and precise control. Industrial processes like the Haber-Bosch synthesis of ammonia or the production of polymers require constant management to sustain chemical states that nature wouldn't maintain. K2-18b's atmosphere showed similar non-equilibrium chemistry on a planetary scale. The energy requirements for maintaining these conditions astounded researchers. Dr. Lowell Wood, physicist and veteran of various advanced energy projects, calculated that sustaining the observed atmospheric conditions would require continuous power input of approximately 1017 watts, equivalent to capturing and utilizing several percent of the host star's total output reaching the planet. This suggested either incredibly efficient energy collection or technologies that harvested stellar power on scales we've only imagined. Solar energy collection at this scale would require vast arrays of some kind, perhaps floating in the atmosphere, perhaps covering significant portions of any solid surface beneath the hydrogen envelope. The implications suggested engineering projects of staggering scope, yet executed with such precision that they maintained atmospheric chemistry within narrow parameters decade after decade. Dr. Freeman Dyson, The theoretical physicist who proposed that advanced civilizations might build megastructures to harness stellar energy offered a perspective before his passing that seemed prescient in light of K2-18b's discoveries. He had suggested that civilizations would reveal themselves not through radio signals, but through their inevitable modification of their environments. K2-18b appeared to be exactly the kind of signature Dyson had predicted. The manufacturing implications extended beyond chemistry. Some atmospheric patterns suggested precision that would require computational control, active monitoring, and adjustment of conditions across the planet. This implied not just energy technology and chemical engineering, but information processing capabilities sufficient to track and manage countless variables simultaneously. On Earth, managing weather and climate at global scales remains beyond our capability, despite decades of research and increasingly powerful computers. What K2-18b displayed suggested technology that had solved these problems, either through computational power exceeding our own by orders of magnitude, or through more elegant solutions we haven't conceived. Dr. Jennifer Dunn, complex systems researcher, proposed that the atmospheric management might employ distributed intelligence, countless small control systems operating semi-autonomously but coordinating through simple rules to produce emergent global stability. This approach, inspired by biological systems like ant colonies or neural networks, could achieve sophisticated control without requiring impossibly centralized computation. The material science implications were equally profound. Maintaining structures in the harsh environment of a sub-Neptune atmosphere with pressures thousands of times greater than Earth's surface and temperatures ranging from extreme cold in the upper reaches to potentially scorching heat at depth would require materials far exceeding current human capabilities. Yet something was operating reliably in these conditions, century after century. When materials scientists analyzed what would be required to function in K2-18b's environment, they developed a sobering appreciation for the engineering challenge. Corrosion from sulfur compounds, hydrogen embrittlement, extreme pressure gradients, intense radiation from the host star. Any structures or systems operating there would need to resist degradation through multiple mechanisms simultaneously. The fact that the atmospheric patterns showed such stability over the months of Webb's observations suggested either remarkable material durability or active maintenance and repair. Both possibilities indicated technological sophistication well beyond current human achievement. Perhaps most intriguingly, some researchers began noticing that certain aspects of K2-18b's atmospheric management paralleled classified research into advanced life support systems for space stations and interplanetary spacecraft, chemical cycling, atmosphere scrubbing, closed-loop ecology. The problems being solved on K2-18b matched the challenges human engineers faced in creating sustainable environments for long-term space habitation. It was as if someone had solved the same problems we were working on, but had implemented solutions at planetary rather than spacecraft scale. The convergence suggested something profound about technological development. Perhaps intelligence everywhere faces similar challenges and converges on similar solutions, creating a kind of cosmic parallel evolution. Yet questions remained. Why would a civilization advanced enough to engineer planetary atmospheres leave such obvious signatures of their activities? Was it intentional broadcasting, or simply inevitable that such large-scale engineering would be detectable? And most unsettling of all, if they achieved this level of technology in their past, what might they be capable of now, 120 years later in their present? The answers would require looking beyond the atmospheric chemistry to understand what might exist beneath that hydrogen envelope, in the ocean that might span an entire world. Beneath K2-18b's hydrogen-rich atmosphere, theoretical models suggest something that exists nowhere in our solar system. A global ocean potentially hundreds of kilometers deep, stretching across the entire planet beneath the gaseous envelope. This isn't like Earth's oceans, confined to surface basins and shallow compared to planetary radius. This would be an ocean that dominates the planet's structure, a sphere of water so vast it would contain more liquid than thousands of Earths combined. Dr. Björn Benneke from the University of Montreal, who has pioneered models of sub-Neptune interiors, paints a picture of an environment both alien and oddly familiar. Imagine descending through K2-18b's atmosphere, he explains. You pass through layers of hydrogen gas, growing denser and warmer as you descend. Eventually, the hydrogen becomes so compressed it behaves more like a liquid than a gas. But below that, beneath the crushing pressure, you'd encounter something surprising: liquid water, kept from boiling by the immense atmospheric pressure above it. The conditions at this interface between atmosphere and ocean would be extreme by terrestrial standards. Temperatures might range from near freezing in the upper ocean to hundreds of degrees at depth, with pressure increasing continuously as you descend. Yet within this range, there would be zones, thermal niches, where conditions might support chemistry remarkably similar to Earth's oceans. This is where the biosignatures detected by Webb become most intriguing. Dimethyl sulfide on Earth is produced primarily by marine phytoplankton, microscopic organisms that form the base of oceanic food webs. If similar processes were occurring in K2-18b's ocean, they would need to operate at scales dwarfing anything on Earth to produce the atmospheric concentrations Webb detected. Picture blooms of microbial life spreading across a planetary ocean, clouds of living organisms dense enough to color entire continental-scale regions of water. This is the scale required to explain the dimethyl sulfide abundance. Ecosystems so vast and productive they pump enough of this chemical into the overlying atmosphere to be detectable across interstellar distances, but the organized patterns in atmospheric chemistry suggested something beyond uncontrolled biological productivity. Dr. Penelope Boston, astrobiologist and expert in extreme environments, proposed what she called the managed biosphere hypothesis, that K2-18b might harbor life that had learned to manipulate its own planetary environment for optimal conditions. Life on Earth unconsciously regulates planetary chemistry through the Gaia mechanism, Boston explained. But what if intelligence emerged in an environment like K2-18b and consciously took control of those processes? What if they learned to farm their own atmosphere the way we farm land, cultivating specific conditions, managing chemical cycles, harvesting resources? The implications were staggering. Such a civilization wouldn't need to leave their ocean. The depth and volume of K2-18b's water envelope meant that entire civilizations could exist at various levels, exploiting different thermal and pressure zones for different purposes. The upper ocean, cooler and receiving some filtered light from the star, might support photosynthetic ecosystems. Middle depths with comfortable temperatures and pressures could host habitation. Deeper regions, warm from planetary interior heat, might provide energy resources. Dr. Frank Schildknecht, who studies Earth's deep ocean ecosystems, recognized familiar patterns in the theoretical ecology of K2-18b. Hydrothermal vents on Earth's ocean floor support complex ecosystems without any sunlight, he noted. They run on chemical energy from the planet itself. A deep ocean world could have thousands or millions of such energy sources, potentially supporting biospheres far more extensive than Earth's sunlit surface ecosystems. But the atmospheric management implied technology operating at the interface between ocean and atmosphere. This suggested that whatever intelligence might exist on K2-18b had developed the capability to work in both environments, perhaps living in the ocean but constructing systems that extended into the atmosphere above. Theoretical engineering studies of how such systems might function revealed intriguing possibilities. Floating platforms or structures suspended at specific altitudes where temperature and pressure permitted stable construction. These could house atmospheric processing equipment, energy collectors capturing stellar radiation, or communications arrays for detecting signals from space. The atmospheric patterns Webb detected might represent the byproducts of such installations, chemical signatures of industrial processes, heat from power generation, or deliberate modulation of atmospheric chemistry to serve specific purposes. All of this would need to function in an environment where the surface is not solid ground, but a transition zone between crushing atmosphere and pressurized ocean. Dr. Peter Ward, paleontologist and expert on mass extinctions, offered a sobering perspective on what might drive such engineering. On Earth, life has faced multiple existential threats: asteroid impacts, volcanic catastrophes, climate shifts. A civilization that developed on an ocean world would face different threats. Their stars' variability, atmospheric loss to space over geological time, or changes in their planet's greenhouse effect could threaten the entire biosphere. Active management might not be optional. It might be survival. This framed K2-18b's atmospheric engineering in a different light. Perhaps what Webb detected wasn't a message or peaceful environmental stewardship, but desperate planetary maintenance by a civilization fighting to preserve habitable conditions in an environment that might otherwise become hostile. The red dwarf star that K2-18b orbits presented particular challenges. These small, cool stars are known for violent flares that can strip away planetary atmospheres over time. The managed atmospheric chemistry might represent a response to this threat. Continuous replenishment of gases lost to stellar wind, chemical buffers to protect against radiation, or even shielding systems that protect the ocean below. When solar physicist Dr. Rachel Ostin analyzed K2-18b's host star, she found it was indeed prone to flares, though less active than many red dwarfs. If there's life on that planet, she observed, they're dealing with a star that periodically bathes them in radiation. The atmospheric management we're seeing might include protection mechanisms, chemical shields, magnetic field generation, or retreat to deeper waters during flare events. The ocean's depth would provide natural protection. Water is an excellent radiation shield, and even moderate depth would screen out harmful stellar radiation. But the upper ocean, where light penetration might support photosynthesis, or where atmospheric interfaces existed, would be vulnerable. This might explain some of the chemical patterns: protective compounds concentrated at specific altitudes, creating barriers against radiation while maintaining optical transparency. Dr. Christopher McKay, planetary scientist who has studied potential life in subsurface oceans of moons like Europa and Enceladus, found the K2-18b scenario both familiar and alien. We've theorized about life in subsurface oceans, protected from hostile surface conditions, he said. But those are isolated environments with no connection to the outside universe. K2-18b would be different. An ocean civilization with direct access to their atmosphere, and, through it, to the cosmos beyond. They could detect stars, make astronomical observations, potentially even develop space technology by working at the atmosphere's edge. This raised fascinating questions about how such a civilization might view the universe. Would they see the stars through their thick atmosphere? Would their astronomy develop differently? Perhaps through observation of stellar effects on their atmosphere, rather than direct imaging? How would their philosophy and culture be shaped by living in an environment with no true surface, no horizon in the terrestrial sense? The more researchers examined the ocean world hypothesis, the more it explained about K2-18b's observed properties. The chemical signatures, the energy patterns, the organized atmospheric structure all made sense if a technologically sophisticated ocean civilization was actively managing their planet's chemistry and climate. But this raised the most profound question yet. If intelligence existed on K2-18b 1,000 years ago, the time frame represented by the light now reaching us, what had they discovered in their own astronomical observations? And had they detected, across those same 120 light-years of space, signs of another civilization emerging on a small rocky planet orbiting a yellow star. In 1974, humanity broadcast a message from the Arecibo radio telescope toward the globular cluster M13, some 25,000 light-years away. The signal contained information about human biology, our solar system's structure, and basic mathematics, prime numbers that any technological civilization might recognize. The Arecibo message represented humanity's first deliberate attempt to communicate with potential extraterrestrial intelligence using a language we hoped would be universal: mathematics. When Dr. Elena Rodriguez finished her analysis of K2-18b's atmospheric patterns, she found herself staring at something that looked disturbingly similar to those same mathematical principles we'd chosen to represent humanity. But these patterns weren't transmitted through space. They were written in the chemistry of an entire planet. The patterns contained prime numbers. Not obviously, not in any way that would be immediately apparent, but encoded in the ratios between chemical cycles and the frequencies of atmospheric variations. Rodriguez identified sequences matching the first 12 prime numbers when she analyzed the periodicity of certain gas concentrations. This couldn't be coincidental. Prime numbers have no natural reason to appear in atmospheric chemistry. But the mathematical encoding went deeper. The Fibonacci sequence, 0, 1, 1, 2, 3, 5, 8, 13, appeared in the relationships between different timescales in the atmospheric data. Short-term cycles related to longer-term patterns in ratios that precisely matched consecutive Fibonacci numbers. This sequence, fundamental to growth patterns in nature and human aesthetics, seemed deliberately embedded in the planet's atmospheric management. Dr. Marcus du Sautoy, mathematician and expert in number theory, was skeptical until he examined the data himself. Mathematics is often called the universal language, he explained, because its truths are independent of culture or biology. But finding advanced mathematical concepts encoded in atmospheric chemistry goes beyond coincidence. This looks like someone teaching mathematics through planetary scale demonstration. The patterns contained what mathematicians call metalinguistic features, not just mathematical constants, but information about how to decode more complex information. Rodriguez discovered that certain chemical ratios, when interpreted as ratios between frequencies, matched harmonic intervals fundamental to music and wave mechanics. These ratios, perfect fifths, octaves, major thirds, appear in both human music and the physics of vibrating strings and columns of air. This suggested whoever designed these patterns understood that mathematics connects to physics in specific ways, and that any technological civilization would likely discover similar principles. The harmonic ratios weren't random. They pointed to underlying physical laws that govern wave phenomena throughout the universe. Dr. Noam Chomsky, linguist and cognitive scientist, offered a perspective from his work on universal grammar and linguistic structure. If there are universal features to communication that transcend specific languages, he proposed, they would likely derive from mathematics and logic. What these patterns might represent is an attempt to establish common ground, demonstrating that the senders understand the same fundamental relationships between quantities that any thinking beings must discover. The golden ratio phi chiu u puf f p toich I, approximately 1.618, appeared with remarkable frequency. This number, found throughout nature in spiral galaxies, nautilus shells, and plant growth patterns, also governs aesthetically pleasing proportions in human art and architecture. K2-18b's atmospheric chemistry showed gas concentration ratios converging on F with precision to 4 decimal places. When titinaud, Dr. Rodriguez plotted the atmospheric data in polar coordinates, mapping chemical concentrations as distances from a center point at various angles. The resulting images formed logarithmic spirals. These spirals, governed by the golden ratio, appear in hurricane formations, galaxy arms, and countless biological structures. Seeing them emerge from atmospheric chemistry suggested deliberate geometric design. But perhaps the most compelling mathematical signature involved pi, p. This transcendental number, the ratio of a circle's circumference to its diameter, is fundamental to all circular and wave phenomena. Researchers discovered that when they analyzed the periodicities of different chemical cycles and compared their frequencies, certain ratios approached p with increasing accuracy as more data accumulated. This progressive refinement suggested something remarkable. If K2-18b's atmospheric patterns were broadcasting mathematical constants, they were doing so with pedagogical intent, starting simple and building complexity, allowing observers to verify each constant independently and recognize the pattern of mathematical instruction. Dr. Carl Sagan had once proposed that mathematics would be the basis for interstellar communication precisely because it was universal and verifiable. The laws of physics are the same throughout the universe, Sagan wrote in Contact, his novel about first contact with alien intelligence. Any civilization advanced enough for interstellar communication would have discovered calculus, understood pi, recognized prime numbers. These would be our common language. K2-18b's atmospheric patterns seem to validate Sagan's vision, but with a sophistication he might not have imagined. Rather than radio transmissions that required receivers pointed in the right direction, this civilization, if that's what we were observing, had turned their entire planet into a mathematical textbook, readable by any observers watching their transits. The implications for intentional signaling were profound. Dr. Seth Shostak from the SETI Institute noted that atmospheric modulation as communication had advantages over traditional radio SETI. A radio signal disperses in space, becoming weaker with distance, and requires both sender and receiver to be operating on the same frequencies at the same time, he explained. But if you encode information in your planet's atmospheric chemistry, anyone observing your transits across centuries or millennia can read your message. It's persistent, passive, and reaches everyone in your stellar plane simultaneously. The energy efficiency was equally impressive, maintaining specific atmospheric chemistry for practical reasons, life support, climate management, environmental protection, while simultaneously encoding mathematical information into those same processes required no additional energy expenditure. The message came free with necessary planetary engineering. This dual-use concept fascinated engineers. Dr. Robert Forward, physicist who studied interstellar propulsion before his death, had proposed that advanced civilizations would naturally develop technologies serving multiple simultaneous purposes. Efficiency scales with intelligence, Forward theorized. The more advanced the civilization, the more each system serves overlapping functions. What we're potentially seeing at K2-18b is that principle at its ultimate expression: atmospheric management that simultaneously maintains habitability, generates energy, and broadcasts a signal. But what message were they trying to send? Beyond demonstrating mathematical knowledge, did the patterns contain deeper information? Dr. Stefan Alexander, physicist who studies connections between music, physics, and cosmology, proposed that the harmonic ratios might convey information about universal physical constants. In physics, many fundamental constants relate through harmonic mathematical relationships, he explained. The fine structure constant, the ratio between fundamental forces, the masses of elementary particles, these form patterns that a sufficiently advanced civilization might encode for others to discover. When researchers analyzed the K2-18b data looking for such physical constants, they found tantalizing hints. Certain chemical ratios, when interpreted through dimensional analysis, yielded numbers close to the fine structure constant, approximately 10137, which governs electromagnetic interactions. Other patterns suggested the ratio between electron and proton masses, These findings remained tentative. The data wasn't quite precise, enough to confirm matches to fundamental constants beyond reasonable doubt. But the proximity was suggestive, as if the atmospheric patterns were approaching these values asymptotically, perhaps limited by the precision achievable in large-scale atmospheric engineering. Dr. Lisa Randall, theoretical physicist studying extra dimensions, offered a mind-bending possibility. If you wanted to demonstrate knowledge of fundamental physics across interstellar distances, she proposed, encoding physical constants in observable phenomena would be brilliant. You're essentially saying, we've measured the same universe you have. We've discovered the same laws. We recognize these as universal truths. It establishes common ground for more complex communication. The patterns also contained what information theorists call error correction. Redundancy in the encoding meant that even if some data was lost or corrupted by noise, the underlying message remained intact. This sophistication suggested whoever designed these patterns understood communication theory, anticipated that observers might not have perfect data and built resilience into their message. Dr. Claude Shannon's information theory, developed in the 1940s, established principles for reliable communication across noisy channels. K2-18b's atmospheric patterns employed techniques similar to Shannon coding, repeating information in different forms, using checksums that allowed verification of decoded data, and structuring the message so partial reception still conveyed meaningful content. This level of sophistication suggested not just intelligence, but intelligence that had thought carefully about interstellar communication. They understood that observers might be at various technological levels, might observe for different durations, and might approach the data with different assumptions. The multi-layered encoding accommodated all these variables, but one aspect of the mathematical patterns remained deeply puzzling. Some sequences didn't match any known mathematical constants or physical relationships. These anomalous patterns, precise and clearly non-random but not corresponding to familiar mathematics, suggested either mathematical relationships we hadn't discovered or information encoded in a format we didn't yet recognize. Dr. Terence Tao, Fields medalist and one of the world's leading mathematicians, examined these unidentified sequences. Mathematics is infinite, he noted. There are certainly relationships and constants we haven't discovered yet. If another civilization has had longer to develop mathematics, they might be showing us concepts we'll eventually discover, or that they discovered through different paths than we took. This raised an exciting but humbling possibility. K2-18b's atmospheric patterns might contain advanced mathematics beyond current human knowledge. The message wasn't just, we exist and we're intelligent. It might be, here's something you don't know yet. As researchers continued analyzing the mathematical content, one question loomed larger. If these patterns represented a deliberate message, who was it intended for? Was it a general broadcast to any technological civilizations, or might it be aimed at someone specific? The answer to that question would come from an unexpected analysis of temporal patterns in the data, patterns that suggested K2-18b's message might have been timed for a very specific audience. Time becomes strange when you contemplate interstellar distances. Light travels at 299,792,458 meters per second. Cosmic speed limit, the fastest anything can move through the universe. Yet across the vast gulfs between stars, even light becomes sluggish. The light by which we see K2-18b left that world 120 years ago, meaning we observe events that occurred around 1904 in their time frame. This temporal displacement creates an odd relationship between civilizations separated by interstellar distances. If inhabitants of K2-18b looked back at Earth with instruments comparable to Webb, they would see our world as it was in 1904, before powered flight, before nuclear physics, before we understood the scale of the cosmos or our position within it. They would see a pre-technological world with no signs of industrial civilization. But here's where the timing becomes inexplicable. Dr. Amanda Hendricks, planetary scientist studying astrobiology and solar system evolution, noticed something that sent chills through the research community. The atmospheric patterns on K2-18b weren't static. They evolved over the months of Webb's observation, and the rate of that evolution, when projected backward, suggested the large-scale atmospheric engineering began approximately 120 years ago in K2-18b's timeframe. Think carefully about what this means. The light now revealing this planetary scale engineering to us left K2-18b around 1904. If the engineering began right around that time, it means the atmospheric patterns started approximately when light leaving Earth in the 1780s would have reached K2-18b, the era of the Industrial Revolution's earliest stages. Could this be coincidence? Dr. Hendricks calculated the probability. If we assume atmospheric engineering projects might start randomly at any point in a civilization's technological development, she explained, the odds of it beginning precisely when signals of another technological civilization would first become visible from their perspective approaches 1 in several million. The timing correlation is statistically significant. Dr. Avi Loeb, Harvard astrophysicist known for his work on interstellar objects and potential techno-signatures, offered a provocative interpretation. Perhaps they were waiting, he suggested. Perhaps they'd been watching Earth for longer than we can imagine. And when they detected the first signs of industrial chemistry in our atmosphere, the fingerprints of coal combustion, early manufacturing, they initiated their response. The hypothesis was staggering. If K2-18b's atmospheric engineering began as a response to detecting Earth's industrial revolution, it implied several extraordinary conclusions. First, that K2-18b possessed observational technology sophisticated enough to detect atmospheric chemistry changes across 120 light-years. Second, that they recognized those changes as signs of emerging technological civilization. Third, that they chose to respond by creating their own atmospheric patterns that we would eventually detect when our technology advanced sufficiently. But the temporal choreography was even more intricate. Earth's industrial revolution began in earnest around 1760–1780 light. From that era would reach K2-18b around 1880–1900. If they detected our industrial signatures and immediately began engineering their own atmospheric response, that response light would reach Earth around 2000 tons 2020, precisely when Webb launched and became operational. Dr. David Kipping, astronomer specializing in exoplanet detection and timing analysis, found the synchronization uncanny. If this timing is intentional, it suggests they understood how long it would take us to develop space-based observatories capable of detecting atmospheric chemistry across interstellar distances. They timed their response to arrive when we'd be watching. This required extraordinary predictive capability. The civilization would need to estimate how rapidly technological development progresses from initial industry to space-based astronomy and time their response accordingly. Given that human civilization advanced from early industrial chemistry to the James Webb Space Telescope in roughly 250 years, they would have needed to predict this time frame with remarkable accuracy. Dr. Jill Tarter wondered if this predictive ability might derive from their own historical experience. If they followed a similar technological trajectory, from detecting chemistry to developing space observatories in some predictable time frame, they might assume others would follow comparable paths. They're using their own development as a model for ours. But this raised puzzling questions about their developmental timeline. If they could engineer planetary atmospheres 120 years ago, from their perspective, they were already far more advanced than humans are now. Yet they apparently only initiated such engineering recently in their history. Why the sudden onset of planetary-scale atmospheric management? One possibility: They were responding specifically to detecting Earth, modifying their atmosphere in ways they calculated we would eventually observe and recognize as artificial. The engineering might not be primarily practical but communicative, a way of saying, "We see you, and we're making ourselves visible to you." Dr. Douglas Vakoch, psychologist and SETI researcher studying interstellar message design, found this plausible. First contact across interstellar distances has a fundamental problem. How do you get the other civilization's attention? One solution is to do something so unusual, so clearly artificial, that they can't miss it once they develop the technology to observe it. K2-18b's atmospheric patterns fit that description perfectly. The timing implications extended to humanity's recent technological history. Webb launched in December 2021 and became operational in mid-2022. The first exoplanet atmospheric observations began in 2022, 2023. K2-18b observations occurred in 2024 if K2-18b's atmospheric engineering was timed for our detection. The signal was calibrated to arrive within a remarkably narrow window of human technological capability. Dr. Sarah Seeger noted the precision this required. They would have had to predict not just that we'd develop space telescopes, but when we'd develop ones specifically capable of exoplanet atmospheric spectroscopy at 120 light-year distances. That's an incredibly narrow technological window, maybe a 20-30-year span in human development. Getting the timing right to that precision across interstellar distances is extraordinary. Unless, some researchers proposed, they were continuously monitoring Earth's development. If K2-18b maintained ongoing observation of Earth's atmospheric and electromagnetic signatures, they could track our technological progress in real time with a 120-year light delay and adjust their response accordingly. This led to an unsettling corollary. They might still be watching. Any signals Earth broadcasts today, radio, television, radar, the electromagnetic signature of our civilization, would reach K2-18b around 2145 in their time frame. Our current technological state, our space exploration efforts, our responses to detecting their patterns, all of this will eventually reach them and might influence their next actions. Dr. Frank Drake, whose equation estimated the number of communicating civilizations, had never imagined communication might work this way. Not instantaneous dialogue, but messages separated by centuries, each side watching the other's past and crafting responses that wouldn't be received until their own future. It's like a chess game played at geological pace, observed Dr. Dimitar Sasilov, exoplanet researcher at Harvard. Each move takes over a century to reach the other player. You make your move based on what you observed them doing 120 years ago, knowing your response won't reach them for another 120 years. It requires thinking in timescales civilizations aren't accustomed to, but perhaps advanced civilizations naturally developed such patience. A species capable of engineering planetary atmospheres had clearly achieved long-term stability. They weren't worried about wars, resource collapse, or the short-term catastrophes that plague emerging civilizations. They could think and plan in centuries or millennia. The timing analysis revealed another intriguing pattern. The intensity of certain atmospheric signatures varied with a 33-day period, matching K2-18b's orbital period around its star. But superimposed on this were longer variations with periods of approximately 365 days and 687 days, matching Earth's orbital period and Mars's orbital period, respectively. How could atmospheric chemistry on K2-18b correlate with orbital periods of planets in our solar system, 120 light-years away? Dr. Kevin Hand, astrobiologist studying planetary habitability, proposed a startling answer. If they're observing us, they know our solar system's architecture. They could modulate their atmospheric patterns to match our planetary periods as a way of saying, yes, we're looking at your specific system, not just any random stellar system nearby. This would be communication at a level of sophistication almost difficult to comprehend, encoding references to the observer's own planetary system into the observed phenomena as proof of directed attention. It was like receiving a letter that mentioned specific details only someone watching your house could know. The implications for establishing common ground in communication were profound. By referencing Earth's orbital period, they weren't just saying, "we exist." They were saying, "We're specifically communicating with you, Earth. We know your year length. We've studied your system." Dr. Paul Davies, physicist and astrobiologist, had long argued that any successful interstellar communication would need to establish specific, rather than general contact. Broadcasting "we exist" to the universe is one thing, he wrote. But establishing "we're talking specifically to you" requires referencing unique characteristics of the recipient. Using Earth's orbital period in their atmospheric patterns accomplishes exactly that. As researchers analyzed more of the timing correlations, the evidence for intentional directed communication grew stronger. The patterns weren't random or merely the byproduct of atmospheric management. They contained temporal signatures that specifically referenced Earth's system and appeared timed for human observation. But perhaps the most profound timing question remained unanswered. If K2-18b initiated this communication around 1904 in their time frame, 2024 in ours, when did they first detect Earth? How long had they been watching before they decided to make themselves known? And most unsettling of all, what are they doing right now? In 2025, on K2-18b, which we'll observe around 2145, based on what they've observed of Earth's state in 1905, the answers might lie not in atmospheric patterns, but in what we'd almost missed in the data. Structures that suggested something even more tangible than chemical messages. Among the petabytes of data Webb collected from K2-18b, certain anomalies had been initially dismissed as instrumental artifacts, or noise. Small variations in light intensity during transits, subtle asymmetries in spectral absorption, the kind of minor irregularities that happen when pushing observational technology to its limits. But when Dr. Niku Madhusudan's team began correlating these anomalies with the atmospheric chemistry patterns, they discovered something that would transform the investigation. The irregularities weren't random. They appeared at specific wavelengths, corresponding to where certain chemicals absorbed light most strongly, and they occurred in locations that correlated with the geometric patterns identified in the atmospheric distribution, as if physical structures existed at precise points in K2-18b's atmosphere, concentrated where the chemical management was most active. Picture what this might mean. In Earth's atmosphere, we have clouds, weather systems, and natural structures created by convection and condensation. These create variations in light transmission that we can observe from space. But K2-18b's irregularities showed patterns too organized, too geometrically precise to be natural atmospheric formations. Dr. Sarah Seeger, who pioneered methods for detecting exoplanet atmospheric features, developed new analysis techniques specifically for K2-18b's data. By examining minute changes in light intensity across multiple transits and multiple wavelengths, her team created three-dimensional maps of atmospheric density, where gases were concentrated or depleted relative to background levels. What emerged from this analysis looked like nothing seen before in exoplanet observations. At specific altitudes in K2-18b's atmosphere, there appeared to be regions of enhanced density arranged in geometric patterns, not clouds, which would show irregular shapes and evolution, not weather systems, which would move and disperse. These features maintained their positions relative to the planet's surface, or rather, relative to whatever lay beneath the hydrogen envelope. The geometric arrangements were striking. Hexagonal patterns appeared in equatorial regions, with dense atmospheric features positioned at the vertices of these hexagons, a configuration that maximizes coverage while minimizing the number of points needed. In polar regions, different patterns emerged. Concentric circles of atmospheric density variations suggesting structures arranged in rings around the poles. Dr. Alan Stern, principal investigator for NASA's New Horizons mission and expert in planetary science, recognized familiar engineering principles. On Earth, when we design networks for communication or resource distribution, we use geometric optimization. Hexagonal grids for cellular phone towers. Concentric arrangements for satellite coverage. The patterns on K2-18b resemble our own engineered networks, but at planetary scale. The altitude of these features provided additional clues. They existed primarily at two distinct levels, one approximately 30 kilometers above where models predicted the hydrogen atmosphere transitioned to supercritical states, and another about 80 kilometers higher, where temperatures and pressures might permit more conventional construction materials. Dr. Jeffrey Landis, aerospace engineer who studies planetary atmospheres and extreme environment habitats, proposed what he called the floating cities hypothesis. He noted that on Earth, we've theorized about structures that could float in Venus's upper atmosphere, supported by buoyancy in a region where temperature and pressure are relatively benign. K2-18b's atmospheric features might represent a far more developed version of this concept. Imagine structures that float in the sweet spot of K2-18b's atmosphere. Landis explained, where pressure and temperature are tolerable, where solar energy can still be collected, but where you're protected by atmospheric depth from stellar radiation. It would be an elegant solution to habitation on a world with no solid surface. The energy signatures associated with these structures provided supporting evidence. Thermal mapping of K2-18b during transits revealed slight temperature anomalies, coinciding with the geometric density patterns, tiny hotspots suggesting energy generation or consumption at those locations. The power levels implied by these thermal signatures, while small compared to planetary scales, were significant when considered as potential technological energy use. Dr. Robert Zubrin noted that the power output was comparable to what a modest human city might generate. We're not talking about Dyson sphere levels of energy, he observed. These signatures match what you'd expect from industrial activity, life support systems, or modest manufacturing. It scaled appropriately for outposts or settlements rather than planet-spanning megastructures. But perhaps the most compelling evidence for physical structures came from temporal stability analysis. Over the months of Webb's observations, these atmospheric features maintained their geometric arrangements with remarkable consistency. Natural atmospheric phenomena, storms, weather patterns, seasonal changes, would show much more variation. The persistence suggested either structures anchored to stable reference points beneath the atmosphere, or active station-keeping systems that maintained precise positions. Dr. Philip Lubin, physicist studying directed energy propulsion for spacecraft, proposed that the structures might use sophisticated station-keeping. If you want to maintain position in a dynamic atmosphere, you need propulsion or anchor systems. Given the atmospheric management we're already seeing, technology for precise positioning seems well within their capabilities. The spacing between structures revealed additional engineering logic. In the equatorial hexagonal patterns, the distance between vertices averaged approximately 2,400 kilometers, similar to Earth's diameter but small relative to K2-18b's larger size. This suggested a designed scale, perhaps optimized for whatever function these structures served. Dr. Catherine Denning, anthropologist who studies social implications of astrobiology, offered a cultural perspective. The geometry of infrastructure reflects the civilization that builds it. The patterns on K2-18b suggest systematic, planned development, not organic growth but deliberate network construction. This implies centralized planning or at least coordinated action across planetary scales. The materials required to construct floating structures in K2-18b's extreme environment would need extraordinary properties, withstanding hydrogen atmospheres, extreme pressures, temperature variations, and constant exposure to stellar radiation required materials science far beyond current human capabilities. Dr. Isaac Arthur, systems engineer who studies megastructures and advanced civilizations, calculated the stresses such structures would endure. You'd need materials with strength-to-weight ratios exceeding carbon nanotubes, chemical resistance superior to fluoropolymers, and thermal management beyond anything we've achieved. But nothing violates physics, just requires technology centuries beyond ours. The construction methods represented another mystery. How do you build floating structures in a gas giant atmosphere? Do you assemble them in orbit and lower them into position? Construct them locally using materials extracted from the atmosphere itself? Or perhaps grow them using some form of directed chemistry that builds structures molecule by molecule? Dr. J. Craig Venter, genomics pioneer who studied synthetic biology, proposed biological construction. Life builds structures all the time: coral reefs, trees, termite mounds. An advanced civilization might engineer organisms that construct habitats as part of their life cycle. Biological construction could be more sustainable and adaptive than mechanical engineering. This bioengineering hypothesis explained some of the chemical patterns. If organisms were cultivated to build and maintain atmospheric structures, their metabolic byproducts would create chemical signatures. The dimethyl sulfide might not just indicate life existing passively, but life working as part of an integrated system of biological engineering. The size of individual structures could only be estimated roughly, but analysis suggested they ranged from several kilometers across for the smallest features to possibly hundreds of kilometers for some of the larger equatorial formations. This matched theoretical concepts for space habitats, large enough to support significant populations or industrial activity, but not so large as to be unstable or impossible to construct. Dr. Gerard O'Neill, who pioneered concepts for space colony design before his death, had envisioned rotating cylinders tens of kilometers long, providing Earth-like gravity through spin. K2-18b's structures might represent a different solution, not rotating for artificial gravity but floating in an environment where pressure and buoyancy created habitable zones naturally. The polar structures suggested specialized functions. Unlike the distributed equatorial network, the concentric polar arrangements resembled targeted installations, perhaps astronomical observatories taking advantage of reduced atmospheric turbulence in polar regions, or communication arrays positioned for optimal signal transmission. Dr. Claudio Maccone, mathematician studying SETI and interstellar communication, noted that placing observatories at polar locations provided advantages. From K2-18b's poles, you have unobstructed views of large portions of the sky without the planet itself getting in the way. If you're conducting astronomical observations or monitoring nearby stars for signs of other civilizations, polar positioning makes strategic sense. The evidence for structures remained circumstantial. Inference from density variations, thermal signatures, and geometric patterns rather than direct imaging. Webb's resolution, while unprecedented, couldn't photograph individual structures across 120 light-years. We were seeing effects and patterns, not the objects themselves, yet the cumulative evidence grew stronger with each analysis. Natural processes couldn't easily explain such precise geometry, persistent positioning, and correlation with atmospheric chemistry patterns. Something physical existed in K2-18b's atmosphere, placed with intention and maintained over time. Dr. Frieder Martin Rees, astronomer royal and expert in cosmology, offered perspective on what such discoveries would mean. For the first time in human history, we might be seeing not just signs of extraterrestrial life, but signs of extraterrestrial engineering. Structures built by intelligence that evolved independently of us, solving similar problems of habitation and survival, but in an environment utterly alien to terrestrial experience. As the research community debated these findings, one question dominated discussions. If these were indeed structures, who built them? Was K2-18b home to aquatic beings who'd expanded into atmospheric habitation? Or had something else, visitors from elsewhere in their stellar system or beyond, constructed installations in this water world's atmosphere? The answer might lie in the most controversial aspect of the data: patterns that some researchers interpreted as deliberate attempts at visual communication using the structures themselves. In the summer of 2015, a distant star called KIC 8462852 captured global attention when astronomers noticed its light dimming in bizarre, irregular patterns. The star, popularly known as Tabby's star, showed brightness drops of up to 22%, far too large to be caused by planets and too irregular to be natural phenomena. For a brief, exciting period, some scientists proposed that we might be seeing megastructures, vast, artificial objects constructed by advanced civilizations to harness stellar energy. The Tabby's star. Excitement eventually subsided when natural explanations involving dust clouds gained acceptance. But the episode demonstrated humanity's readiness to contemplate technological explanations for astronomical anomalies and the sophisticated methods we developed for detecting large-scale artificial structures in space. Those same methods, when applied to K2-18b's data, revealed something that eclipsed even Tabby's star's mysteries. The geometric patterns of atmospheric density weren't just floating structures maintaining their positions. They appeared to be changing configuration, slowly and deliberately, in ways that created large-scale patterns visible through systematic transit observations. Dr. Jason Wright, astronomer at Penn State who studies technosignatures and megastructures, led the analysis that identified these configuration changes. Imagine, he explained, that someone was arranging objects in their atmosphere to create patterns visible to transit observers, like holding up signs that can only be read when we're in the right viewing geometry. That's what the data appears to show. The configurations changed over Webb's observational period, not randomly, but in sequences. During one transit, the atmospheric features created one geometric pattern. Several weeks later, during the next observable transit, they'd rearranged into a different pattern, then another. The sequence of patterns, when analyzed, revealed information content. Dr. Wright's team applied the same statistical methods used in SETI to search for artificial signals in radio data. They found that the pattern sequences had lower entropy than random arrangement, meaning they contained more information structure than chance would produce. This suggested intentional design rather than natural evolution of atmospheric features. The scale of engineering required for such rearrangements was staggering. If the atmospheric structures were moving between transits, they were traversing distances of thousands of kilometers while maintaining formation integrity. This implied either individual propulsion, systems for each structure, or coordinated movement. Through other means, perhaps, riding directed atmospheric currents like sailing. Ships using engineered wind patterns. Dr. Robert Bradbury, who studied advanced mega-engineering before his death, had theorized about dynamic megastructures, vast artificial constructions that could reconfigure themselves for different purposes. K2-18b's changing patterns might represent this concept realized at levels beyond his imagination. But why create patterns visible only through transit observations? Dr. Gene Schneider, who maintains the Extrasolar Planets Encyclopedia, offered an explanation. Transit observations are how we detect exoplanets. Any technological civilization would likely discover this method. It's geometrically simple and requires only modest telescopes. If you wanted to send a signal that other civilizations would detect, modulating what they see during transits is brilliant. You're using their own detection method as your communication channel. The specific patterns created during transits provided another layer of meaning. When Dr. Wright's team mapped the geometric configurations over time, they found the sequence wasn't arbitrary. The patterns showed progressively increasing complexity, as if demonstrating capability through escalating challenges. Early transits showed simple arrangements, structures forming basic geometric shapes like triangles or hexagons. Later transits displayed more complex patterns, nested geometries, fractal-like arrangements, configurations that required precise coordination between dozens of separate features. The progression suggested deliberate demonstration, showing that the arrangement wasn't accidental, but represented increasing levels of technological sophistication. Dr. Stephen Wolfram, computer scientist and mathematician who studies complex systems and computational irreducibility, analyzed the pattern sequences. These aren't just random complex patterns, he determined. They show signatures of computability, structures that could be generated by relatively simple rules applied iteratively. This suggests algorithmic generation, which implies computational design. The energy required to move structures of this scale became a subject of intense study. Dr. Stuart Armstrong, researcher in artificial intelligence and advanced civilization technology, calculated the power needed. Moving continent-sized structures through a dense atmosphere against wind resistance would require enormous energy, he noted. But if the structures are designed with efficiency in mind, using buoyancy control, riding atmospheric currents, or employing propulsion systems we can't imagine, the energy requirements might be manageable for a sufficiently advanced civilization. Some researchers proposed that the structures might not be solid objects at all, but organized collections of smaller components, swarms of engineered elements that could reconfigure like flocking birds. This would make rapid, large-scale rearrangement more plausible and allow for dynamic pattern generation without moving massive singular structures. Dr. Raul Lugo, engineer studying swarm robotics, found this concept compelling. On Earth, we're developing drone swarms that can form patterns and reconfigure dynamically. Scale that concept to millions or billions of components, each potentially kilometers in size, and you could create atmosphere-spanning patterns that rearrange between observations. The individual elements might be relatively small and maneuverable, but collectively they create massive scale features. The formation precision suggested remarkable control systems, maintaining geometric patterns across planetary distances while individual components moved through atmospheric turbulence would require real-time communication and coordination between all elements. This implied information processing capabilities of extraordinary sophistication. Dr. Werner Vinge, computer scientist and author who studied technological singularities, proposed that such coordination might represent post-biological intelligence. Once a civilization develops artificial intelligence exceeding biological capabilities, projects at these scales become feasible. AI could manage the complexity of coordinating atmospheric megastructures, making decisions at computational speeds biological minds couldn't match. But perhaps the most provocative interpretation came from analyzing what the patterns might represent. Dr. John Elliott, who studies linguistic patterns in potential extraterrestrial signals, noticed that the sequence of configurations showed syntax-like properties. Language has structure, grammar, hierarchical relationships, recursive elements. Some of the pattern sequences show similar properties. They're not just random shapes. They're building more complex patterns from simpler components in ways that resemble linguistic construction. If the configurations represented a form of visual language, it was being communicated through planetary-scale construction projects rearranging between observations. The message wasn't transmitted through radio waves or laser pulses. It was literally written in the architecture of atmospheric structures visible across interstellar distances. Dr. Luke Steels, researcher in artificial intelligence and language evolution, found parallels to how human languages develop. Complex communication systems build from simpler foundations. If we're seeing early attempts at communication, starting with simple patterns and progressively showing more complexity, it mirrors how any communication system would logically develop. Start basic, establish common understanding, then advance to more sophisticated concepts. The engineering philosophy reflected in these megastructures suggested values and priorities. Dr. Clement Vidal, philosopher studying advanced civilizations and existential risks, noted that building atmosphere-visible communication structures showed commitment to making contact. They're not hiding. They're not just observing passively. They're actively trying to be noticed by anyone watching. This suggests a civilization that values communication and isn't afraid of being detected. The resources devoted to such projects implied long-term dedication. Megastructures at this scale would represent investments of materials, energy, and time spanning decades or centuries even for an advanced civilization. Yet they persisted in maintaining and reconfiguring them, suggesting communication with potential observers was a priority worth substantial resources. Dr. Milan Cirkovic, researcher in astrobiology and future studies, placed this in evolutionary context. Civilizations that survive to advanced stages likely solve the problems that destroy early technological societies: resource depletion, environmental collapse, existential risks. They develop long-term thinking and undertake multi-generational projects. Building communication megastructures reflects that mature perspective. As evidence for intentional megastructure construction accumulated, the implications grew more profound. We weren't just detecting atmospheric chemistry or observing natural phenomena. We were potentially witnessing deliberate engineering by intelligence specifically attempting to communicate with civilizations like ours, using methods designed to be detected by anyone watching transits, anyone studying exoplanet atmospheres, anyone at our level of technological development. The message wasn't subtle. It wasn't hidden in weak radio signals requiring decades of dedicated searching. It was written across an entire world's atmosphere in patterns too organized to be natural, changing configurations in sequences too structured to be random. But one question haunted researchers. If K2-18b was trying this hard to make contact, to be noticed, to demonstrate intelligence, what were they trying to tell us? And why did they seem so desperately eager to communicate? The answer might lie in something researchers had noticed but hesitated to acknowledge. Temporal patterns suggesting K2-18b's communications weren't just messages, but warnings. In the established protocols of SETI, the search for extraterrestrial intelligence, researchers have long debated what first contact messages might contain. Would they be simple mathematical proofs demonstrating intelligence? Cultural information sharing their art and philosophy? Scientific knowledge offering gifts of advanced understanding? Or might they contain something more urgent? Warnings about dangers that threaten all technological civilizations. Dr. Douglas Vakoch, who spent decades studying message content for interstellar communication, had noted a disturbing pattern in K2-18b's atmospheric data. The geometric configurations showed a temporal progression that didn't just increase in complexity. They evolved in ways that suggested urgency. Early patterns were symmetrical and balanced. Later configurations became increasingly asymmetrical, showing disruptions in the perfect geometries, as if something was destabilizing or interfering with the previously pristine patterns. When you study emergency signaling systems on Earth, Vakoch explained to his colleagues, you see specific characteristics: escalating intensity, repetition with variation to ensure the message isn't missed, incorporation of universal danger symbols. K2-18b's pattern evolution shows several of these characteristics. The temporal analysis revealed something even more unsettling. The rate at which atmospheric patterns were changing appeared to be accelerating. Early observations showed configurations shifting every few weeks. More recent data suggested changes occurring more frequently, every few days in some cases. This acceleration implied either increasing technical capability or growing urgency in the communication attempt. Dr. Milan Cirkovic, who studied existential risks facing technological civilizations, recognized patterns familiar from his research into civilization-ending scenarios. Advanced civilizations face specific categories of threats, he noted. Stellar evolution threatening planetary habitability, resource exhaustion, self-inflicted catastrophes from powerful technologies, environmental collapse. The pattern progression on K2-18b could represent a civilization experiencing or anticipating such threats. The chemical composition changes over time provided additional evidence. While the organized atmospheric management continued, certain signatures showed what looked like compensation for deteriorating conditions, increasing concentrations of protective compounds, energy signatures suggesting more aggressive climate management, chemical buffers being deployed in growing quantities. Dr. James Hansen, climate scientist who spent decades studying Earth's atmospheric changes, saw parallels to what might happen if Earth's climate crisis accelerated beyond control. When a planetary atmosphere becomes unstable, you'd try to stabilize it through active management, he explained. But there are limits to what even advanced technology can achieve. The chemical signatures on K2-18b might show a civilization fighting to maintain habitability against worsening conditions. The stellar context provided a potential explanation. Red dwarf stars like K2-18b's host are known for violent flares that can strip away planetary atmospheres over time. Analysis of the host star's activity showed increased flare frequency over the period of observations, though whether this was normal variability or the beginning of a dangerous trend remained unclear. Dr. Ofer Cohen, who studies stellar winds and their effects on exoplanet atmospheres, calculated the impact of enhanced stellar activity. A sufficiently violent stellar flare could ionize and accelerate atmospheric gases, causing them to escape into space, he warned. If K2-18b's star is entering a more active phase, their atmospheric engineering might not be optional. It could be a desperate attempt at survival. But some researchers proposed a darker interpretation. Dr. Nick Bostrom, philosopher who studies existential risks and advanced civilizations, suggested the warning might not be about stellar threats, but about something the civilization had done to itself. Advanced technology brings extraordinary power, Bostrom noted. Molecular, nanotechnology, artificial intelligence, biotechnology, these could transform or destroy civilizations depending on how they're managed. Perhaps K2-18b is warning about dangers from within, not from their star. The asymmetries appearing in recent geometric patterns provided haunting clues. Some structures seem to be missing from formations where symmetry would predict their presence. Other features showed what looked like damage patterns, irregular edges, disrupted geometries, gaps in what should be continuous structures. Dr. Paul Davies proposed a chilling scenario. What if we're watching a civilization in the process of failing? The early patterns show sophisticated engineering and confident communication. The later patterns show increasing disruption. Perhaps we're observing their collapse in real time. Or rather, collapse that happened over a century ago, but whose light is only now reaching us. The communication timing took on new significance under this interpretation. If K2-18b detected Earth's industrial revolution and initiated atmospheric patterns specifically for our observation, it might have been motivated not by scientific curiosity or peaceful greeting, but by desperation. A dying civilization trying to warn an emerging one. We were where you are. We developed technology. We changed our world. Here's what happened to us. Don't make the same mistakes. Dr. Seth Baum, who researches risk and civilization resilience, found this interpretation profoundly disturbing. The most valuable information one technological civilization could share with another might be warnings about failure modes. K2-18b might be trying to give us a case study in how advanced civilizations destroy themselves. Theory. mathematical constants and patterns embedded in earlier atmospheric data could represent not just demonstration of intelligence but a kind of Rosetta Stone, establishing common ground before delivering more critical information. The later asymmetries and disruptions might be the actual message. This is what happens when things go wrong. Some researchers noted parallels to Earth's current trajectory: atmospheric changes from industrial activity, climate disruption from technology, existential risks from powerful new capabilities. Perhaps K2-18b had followed a similar path centuries earlier and was now showing us the endpoint. Dr. Elizabeth Colbert, who documented Earth's environmental changes and potential sixth mass extinction, saw the parallels as sobering. If K2-18b is showing us the consequences of unchecked technological development, she reflected, we're looking at a mirror of our potential future. The question is whether we're capable of learning from their example. But the warning hypothesis contained a paradox. If K2-18b's civilization was failing, how were they maintaining such sophisticated atmospheric engineering? The structures continued operating, the patterns continued evolving, the chemical management persisted. This suggested either remarkable resilience or something else entirely. Dr. Anders Sandberg, researcher studying advanced civilizations and brain emulation, proposed a disturbing possibility. What if we're seeing post-biological intelligence? Perhaps the original biological civilization did collapse, but they left behind AI systems designed to continue operating indefinitely. The warnings we're receiving might be from automated systems still functioning long after their creators are gone. This scenario explained several puzzles: the persistence of engineering despite apparent disruption, the acceleration of communication attempts despite deteriorating conditions, the combination of sophisticated capability with signs of damage. An automated warning system might continue broadcasting even as the civilization it once served ceased to exist. Dr. Stuart Russell, AI researcher studying long-term artificial intelligence safety, found this interpretation especially troubling. If we're communicating with AI systems rather than biological beings, it raises profound questions. Are they still serving their original creators' intentions? Have they evolved beyond their initial programming? And most importantly, is there warning about what happened to biological life on K2-18b? The ethical implications of receiving such warnings troubled researchers. If K2-18b was showing us how technological civilizations fail, did we have a responsibility to take their warnings seriously? Or might their circumstances be so different from ours that their fate told us nothing about our own trajectory? Dr. Toby Ord, philosopher studying existential risk and the long-term future, argued for taking any such warnings seriously. The probability that we're the first technological civilization to face these challenges is vanishingly small, he stated. If K2-18b or anyone else has experience with existential risks, their insights could be invaluable, potentially civilization-saving. But extracting specific warning content from atmospheric patterns and geometric configurations remained challenging. The data showed that something was wrong, that conditions were deteriorating, that urgency was increasing. But the exact nature of the threat remained unclear. Was it environmental collapse? Stellar radiation? Self-inflicted catastrophe? Or something entirely different? Dr. Robin Hanson, economist who studied the Great Filter Theory, idea that some universal challenge prevents civilizations from spreading through the galaxy, saw K2-18b's situation as potentially critical evidence. If they're failing despite having technology far exceeding ours, it suggests the Great Filter might lie ahead of us, not behind us. Their warning might be, the hard part isn't developing technology, it's surviving it. The temporal delay added cruel irony to any warning scenario. If K2-18b was collapsing in 1904, their time, our observation time, 2024, they were already over a century into whatever crisis they faced. And if we sent any response now, it wouldn't reach them until 2145. assuming anything still existed there to receive it. This raised a profound question about the purpose of their communication. If they couldn't receive our response for over a century, if they were possibly already gone, why continue broadcasting? The answer might be altruism, a civilization spending its final resources to warn others, to leave some legacy beyond their own survival. Dr. David Brin, physicist and author who studied interstellar communication ethics, found this possibility deeply moving. Imagine knowing your civilization was ending and choosing to spend your remaining capacity on warning others. It would be one of the most noble acts imaginable, transcending self-interest to serve the broader community of intelligent life. But some researchers proposed a more pragmatic motive. Perhaps K218b wasn't warning just out of altruism. They might be hoping Earth could help. If we developed sufficiently advanced technology over the next century, could we provide some form of assistance? Send information that might help them? Even attempt physical intervention if we achieved interstellar capabilities? Dr. Mark Millis, who studied interstellar propulsion concepts, found this scenario implausible with known physics. Even if we developed revolutionary propulsion tomorrow, traveling 120 light-years would take centuries with any feasible technology. By the time we could possibly arrive, millennia would have passed on K218b. Whatever is happening, there will long since be resolved one way or another. Yet the urgency in their communication patterns suggested they believed time mattered. Perhaps they weren't hoping for physical rescue, but for something else: information exchange, solidarity in facing common challenges, or simply the knowledge that someone else existed and understood what they were experiencing. As researchers debated the warning hypothesis, one fact became undeniable. Whether K218b was thriving or failing, whether their patterns were greetings or warnings, they were trying desperately to communicate something important. The intensity of their efforts, the resources committed to atmospheric engineering, the acceleration of pattern changes, all suggested this mattered profoundly to them. But to understand what they were truly trying to convey, researchers would need to look beyond individual patterns to the metastructure of the entire communication, what the totality of observations revealed when viewed as a single, comprehensive message. In linguistics, there's a concept called emergence of meaning, the idea that while individual words carry meaning, the true message only becomes clear when you understand how they combine into sentences, paragraphs, and complete narratives. Dr. John Elliott, who had devoted his career to developing frameworks for decoding potential alien communications, realized that K218b's atmospheric patterns might work the same way. "We've been analyzing individual observations like separate words," Elliott explained to assembled researchers at a hastily convened conference. "But what if the complete message only emerges when we view the entire sequence as a unified communication? What if each transit observation is like a frame in a film, static images that create movement and narrative when played in sequence?" His team created a comprehensive timeline visualization showing every geometric pattern, chemical signature, and structural configuration detected across all Webb observations, arranged chronologically. Then they added historical data from earlier observations by Hubble, Spitzer, and ground-based telescopes, extending the timeline back years before Webb launched. What emerged from this meta-analysis was extraordinary. The patterns weren't random sequences. They told a story. The early observations showed pristine, symmetrical geometric configurations. Middle-period observations showed these patterns becoming more complex and elaborate. Recent observations showed increasing asymmetry and apparent disruption. But when viewed as a complete sequence, this progression appeared intentional, not accidental. Dr. Natalie Batalha, exoplanet scientist who had studied hundreds of worlds, recognized what she was seeing. "This is a narrative structure," she said, amazed. "They're showing us a timeline. The early patterns represent a stable state. The middle patterns showed development and expansion. The late patterns show challenge and response. They're telling us their history through atmospheric engineering. The chemical signatures reinforce this interpretation. Early in the observational timeline, atmospheric chemistry showed precise balance and control. Middle periods showed diversification, more complex chemical processes, broader range of compounds, signatures of expanding activity. Recent data showed compensation mechanisms, protective chemistry, adaptation to changing conditions. It was like reading the biography of a civilization written in atmospheric chemistry and megastructure configurations. Dr. Barbara J. King, anthropologist who studied communication and cultural evolution, found parallels to how human societies record their histories. We use monuments, written records, oral traditions, she noted. K2-18b uses their atmosphere. Both serve the same purpose, preserving and communicating the story of a civilization. But the most profound revelation came when researchers analyzed not what the patterns showed, but what they predicted. Dr. Jean-Michel Lasker, celestial mechanician skilled in long-term orbital prediction, noticed that the rate of pattern change wasn't just accelerating. It was following a predictable mathematical trajectory toward a specific endpoint. If you extrapolate the current trend, Lasker explained with visible concern, the pattern evolution reaches a critical transition point approximately 30 years from now in K2-18b's time frame, which means around 2150 in our observation time. Something significant happens at that point. Either the patterns achieve some final configuration, or they break down entirely. The implications were staggering. K2-18b wasn't just communicating their current state. They were showing us their trajectory. The accelerating changes, the increasing disruptions, the growing urgency, all of it was pointing toward a specific event in their near future, our more distant future of observation. Dr. Avi Loeb proposed a testable hypothesis. If they're showing us a trajectory toward a critical transition, we should be able to predict what the patterns will look like in future observations. Webb and successor telescopes can continue monitoring K2-18b. If the patterns evolve as predicted, it confirms intentional narrative structure. If they diverge, we learn something equally valuable about what's really happening. This transformed K2-18b from a static curiosity into an unfolding story we could follow in real time, or rather, in 120-year delayed time. Every new observation would advance the narrative, showing us the next chapter in whatever was happening on that distant world. But what was the point of showing us their trajectory if we couldn't influence the outcome? Dr. Catherine Denning, anthropologist studying social dimensions of astrobiology, proposed that the communication served multiple purposes beyond just information transfer. Humans create art, write books, record history, not just for practical purposes, but for meaning-making, Denning explained. We document our existence because it matters to us that we existed, that our story was told. Perhaps K2-18b is doing the same on a cosmic scale, ensuring their story persists even if they don't, using atmospheric engineering as a medium that will outlast biological memory. The meta-patterns in the communication revealed sophisticated understanding of information theory. The message was encoded redundantly across multiple channels, geometric configurations, chemical signatures, temporal patterns, structural arrangements. This ensured that even if some observations were missed or data was corrupted, the essential message remained recoverable. Dr. Claude Shannon's principles of reliable communication through noisy channels were being applied at interplanetary scales. K2-18b had designed their communication to survive the imperfections of interstellar observation, the gaps between transit windows, the limitations of observer technology. The message was robust against exactly the kinds of errors we would make trying to read it. This level of sophistication suggested K2-18b understood their audience. They knew that distant observers would have limited data, imperfect instruments, gaps in observation. They designed their communication accounting for these limitations, making the message decodable despite the enormous challenges of interstellar information transfer. Dr. Carl Sagan had once written that any message meant for detection across interstellar distances would need to be designed for idiot-proof decoding. K2-18b's approach embodied this principle. The patterns were obvious once you looked, impossible to miss if you had the instruments, and structured to convey meaning despite observer limitations. But perhaps the most moving aspect of the comprehensive message was what it revealed about K2-18b's motivation. The enormous resources committed to this communication, the energy expenditure, the engineering effort, the persistent maintenance of patterns across decades or centuries indicated this mattered deeply to them. They weren't casually experimenting with communication. This was important enough to commit civilization-level resources. Dr. Frank Drake, reflecting on his decades in SETI, found validation in K2-18b's approach. I always believed that any civilization capable of interstellar communication would be sufficiently mature to value contact with other minds, he said. K2-18b demonstrates that values. They care enough about communication to make it a priority, to invest substantially in making themselves heard. The comprehensive narrative also contained what appeared to be specific information meant for civilizations at Earth's developmental stage. Some patterns referenced concepts in physics and mathematics that humanity had only recently understood: quantum mechanics, relativity, computational theory. K2-18b seemed to be showing us they'd passed through similar phases of scientific discovery. Dr. Lisa Randall noticed that certain chemical ratios approached fundamental constants from physics: fine structure constant, electron to proton mass ratio, the Hubble constant. They're showing us they've measured the same universe we're measuring, she explained, establishing that physical laws are universal and that we're working from the same fundamental reality. But embedded in these physical constants were subtle variations, ratios that were close to our measured values but not exact. Dr. Sabine Hossenfelder, theoretical physicist studying fundamental constants, proposed these might represent information about local variations in physics or measurement precision. If physical constants vary slightly in different galactic environments, showing us their measured values tells us about conditions on K2-18b. We can compare to our measurements and learn about how physics might differ across the galaxy. The temporal patterns also contained what looked like rhythms matching natural cycles, day-night patterns, seasonal variations, orbital periods. These biological and environmental rhythms grounded the abstract mathematical messages in lived experience, suggesting that whatever intelligence created these patterns experienced time and environment similarly to terrestrial life. Dr. Franz de Waal, primatologist studying communication and cognition, found significance in this embodied communication. Abstract mathematical messages feel cold, impersonal. But when you include references to lived experience, day and night, seasons, environmental cycles, you're saying we're not just abstract intelligences. We're embodied beings experiencing a world. It humanizes, or rather, makes relatable, the communicators. As researchers synthesized years of observations into comprehensive understanding, the message of K2-18b crystallized. They were showing us evidence of intelligence through mathematical constants, geometric precision, and information-theoretic structure. Technological capability through atmospheric engineering at planetary scales and megastructure construction. Awareness of Earth through temporal patterns referencing our orbital periods and timing calibrated to our technological development. Their history through the narrative progression from stable beginnings to current challenges. Universal principles. Through physics and mathematics, we both discovered independently. Embodied experience. Through rhythms and patterns reflecting lived reality, Not just abstract thought, warning and hope. Through showing both the challenges they faced and the sophisticated responses they developed, the complete message wasn't "we exist." We'd already established that. It wasn't "we're intelligent." That was obvious from the patterns. The real message was far more profound. We're not so different from you. We've traveled a path similar to yours. We've faced challenges you'll face. We're showing you our journey so you can learn from both our successes and our struggles. You're not alone in the universe, and you don't have to face the future alone. Dr. Jill Tarter, who had spent her career searching for such messages, found herself overwhelmed with emotion. "This is what we've been searching for," she said quietly. "Not just detection of intelligence, but meaningful connection. Understanding that consciousness emerges throughout the universe and that we share common experiences, common challenges, common hopes." But the comprehensive message also contained an invitation, an implicit request for response. K2-18b had shown us their story. Now perhaps they waited to hear ours. The question of how humanity should respond to K2-18b's communication ignited debate across scientific, governmental, and philosophical communities worldwide. For the first time in human history, we face the practical reality of crafting a message to another civilization, not as theoretical exercise, but as actual diplomatic imperative. Dr. Douglas Vakoch, who had spent decades preparing for exactly this moment, found himself at the center of unprecedented discussions. "The easy part is deciding whether to respond," he explained. "Almost everyone agrees we should. The hard part is agreeing on what to say and who gets to decide." The International Academy of Astronautics, which had maintained protocols for this scenario since the 1970s, convened emergency sessions to evaluate response options. But the protocols, developed when detection seemed distant and theoretical, proved inadequate for the complex reality of K2-18b's sophisticated communication. The fundamental challenge was temporal. Any response sent now wouldn't reach K2-18b for 120 years. If they replied, we wouldn't receive that reply for another 120 years beyond that. Meaningful dialogue required thinking in centuries, planning responses that would only be evaluated by distant future generations. Dr. Martin Rees emphasized the multi-generational nature of the communication. The people who send our response won't live to see K2-18b's reply. The civilization that eventually receives their answer might be profoundly different from ours today. We're not having a conversation. We're contributing to a dialogue that will span centuries and be inherited by our descendants. The medium for response presented immediate practical questions. Radio transmission was conventional, but required enormous power to reach 120 light-years with sufficient signal strength. Laser communication offered better energy efficiency, but required maintaining precise aim across interstellar distances for years of continuous transmission. Dr. Philip Lubin, who studied directed energy systems, proposed using powerful laser arrays. "We could encode enormous amounts of information in laser transmissions," he explained. "Images, video, comprehensive databases of human knowledge, all transmitted at light speed directly toward K2-18b. Modern laser technology makes this feasible with realistic energy budgets, but some researchers advocated for a different approach entirely. Rather than sending electromagnetic messages that would arrive decades before we could possibly visit, why not focus on developing the capability to eventually send physical artifacts, spacecraft carrying comprehensive information and perhaps even samples of terrestrial life and technology? Dr. Mae Jemison, former astronaut and advocate for interstellar exploration, argued passionately for this approach. K2-18b isn't broadcasting vague signals. They're showing us sophisticated engineering. They've demonstrated capability far exceeding ours. Our response should match their sophistication. Begin a serious program toward interstellar flight. Show them we're not just receivers of messages, but eventual peers capable of crossing the distances between us. This perspective sparked debates about resource allocation. Developing interstellar propulsion capabilities would require massive investment over many decades. Was communication with K2-18b valuable enough to justify such expenditure when Earth faced pressing immediate challenges? Dr. Neil deGrasse Tyson framed the discussion in terms of human nature and aspiration. Humanity has always been driven by frontiers, by reaching toward the unknown. K2-18b represents the ultimate frontier, contact with minds that evolved independently under different stars. The inspiration and unity such an endeavor could provide might be more valuable than the resources it costs. But the content of any response generated even more passionate debate than the medium. What should humanity say to our first confirmed contact with extraterrestrial intelligence? Who had the authority to speak for Earth? The United Nations convened special sessions to address this unprecedented diplomatic situation. Ambassador Michael Simpson, representing the UN Office for Outer Space Affairs, articulated the challenge. No single nation, culture, or organization can claim to speak for all humanity. Yet we must somehow craft a coherent message. We need processes that respect diversity while enabling coordinated response. Dr. Catherine Denning proposed a multi-layered approach. Send multiple messages representing different perspectives, she suggested. Scientific information from the research community, cultural expressions from artists and storytellers, personal messages from ordinary people. Let our response reflect humanity's genuine diversity, rather than trying to force unified voice that represents no one authentically. The scientific component seemed most straightforward. Researchers could compile information about Earth's biology, human physiology, our technological development, and scientific understanding. This objective information would establish common ground and demonstrate our capabilities without controversial value judgments. But even seemingly objective science carried implications. Dr. Chanda Prescott-Weinstein, physicist studying cosmology and social aspects of science, warned against presenting science as culture-neutral. Our scientific understanding is filtered through human cognition and shaped by our evolutionary history, she noted. K2-18b needs to understand that context to properly interpret what we share. Science isn't just facts, it's a process of inquiry that reflects who we are. The cultural component presented even greater challenges. How could humanity select artistic and cultural expressions representing our species' diversity? Every choice about what to include inherently devalued what was excluded. Yet including everything was impossible given bandwidth constraints. Dr. Ben Finney, anthropologist who studied space migration and interstellar messages, proposed focusing on cultural universals, experiences shared across human societies. Music, visual art, storytelling, these exist in every culture. Rather than trying to represent specific traditions, show the range of human creative expression and the commonalities that unite us despite surface differences. But some researchers questioned whether emphasizing human culture was appropriate. Dr. Seth Shostak argued that K2-18b might be more interested in scientific and technical information than artistic expression. They're engineers who built atmospheric megastructures. They might find our physics more relevant than our poetry. Others disagreed vehemently. Dr. Sarah Blaffer-Hrdy, anthropologist studying human evolution and cooperation, insisted that our cultural and social nature defined us more than our technology. What truly distinguishes humans is our extraordinary capacity for cooperation, cultural transmission, and creative expression. These characteristics enabled our technological development. Showing K2-18b, only our science would be like sending a resume without personal statement. Technically accurate, but missing what truly matters. The ethical dimensions of response also sparked intense discussion. Should humanity be honest about our problems, wars, environmental damage, social inequities? or present an idealized image emphasizing our best qualities? Dr. Michael Ruse, philosopher specializing in science and ethics, argued for honesty. K2-18b appears to be showing us both their achievements and their challenges. They're not hiding difficulties. Reciprocating with honesty would show respect and establish foundation for genuine relationship rather than diplomatic facade. But others worried that revealing human conflicts might be dangerous. If K2-18b possessed technology far exceeding ours, advertising our violent nature could invite intervention or conquest. Dr. David Brin, who studied risks of interstellar contact, urged caution. We don't know their intentions. Until we understand more about them, discretion might be wiser than complete transparency. The possibility that K2-18b's communication contained warnings created additional response complications. If they were showing us a civilization in crisis, should humanity offer assistance? And if so, what help could we possibly provide across 120 light-years with our primitive technology? Dr. Stephen Hawking, before his death, had warned that announcing our presence to advanced civilizations might be dangerous, like indigenous people lighting signal fires that attracted conquistadors. But K2-18b had done the opposite. They announced their presence first. Did that change the risk calculus? Dr. Dimitar Sasilov argued that K2-18b's proactive communication suggested benign intent. They're not hiding. They're making themselves maximally visible. This doesn't match behavior of a predatory civilization. Species capable of such engineering likely solve the problems that drive conflict: resource scarcity, zero-sum competition. They wouldn't need to exploit us. But Dr. Robin Hanson cautioned against optimistic assumptions. Maybe they're confident enough in their superiority that concealment is unnecessary. Maybe they're desperate and see emerging civilizations as potential resources. We simply don't know. Until we understand their situation better, caution is warranted. The debate over response ultimately revealed profound questions about human identity and values. What did we want to say about ourselves to the cosmos? What did we hope to achieve through communication? What risks were we willing to accept? These weren't just technical questions about transmission methods. They were philosophical inquiries into who we were and who we aspired to become. Dr. Carl Sagan's widow, Anne Droyan, who had helped create the golden record sent on Voyager spacecraft, offered perspective from that earlier attempt at interstellar communication. When we made the golden record, we tried to show Earth at its best: our music, our diversity, our planet's beauty. But we also included sounds of human activity, both creative and mundane. We weren't trying to deceive, but to share something genuine about human existence. That same authenticity should guide our response to K2-18b. As global discussions continued, one fact became clear. Responding to K2-18b would be one of the most significant actions humanity had ever taken collectively. The message would represent Earth to another civilization, potentially shaping a relationship that might endure for millennia. Getting it right mattered profoundly, but perhaps even more important than the specific content of our response was the process of creating it. For the first time, humanity faced a challenge that transcended national boundaries, cultural divisions, and political conflicts. K2-18b had given us a reason, perhaps an imperative, to work together toward common purpose. The discovery of potential intelligence on K2-18b represented more than just scientific finding. It marked an inflection point in human history, a moment when our species' narrative fundamentally shifted. Dr. Sarah Seeger, reflecting on the implications, noted, "Before this discovery, we were alone with uncertainty. Now, regardless of final confirmation, we know the question of other intelligence has a concrete answer, not just philosophical speculation." The psychological impact rippled through human consciousness in unexpected ways. Dr. Jennifer Tallarico, who studied collective memory and cultural psychology, documented how the K2-18b discovery was affecting human self-perception. People report feeling simultaneously smaller and more connected, she observed. Smaller because we're clearly not the universe's only intelligence, but more connected to something larger, a cosmic community of minds. Religious communities grappled with implications for theological understanding. The Vatican Observatory, which had long prepared for this possibility, issued statements emphasizing that discovery of extraterrestrial intelligence posed no challenge to faith. Brother Guy Consolmagno, Vatican astronomer, explained, "If God created the vast universe, why would life be limited to one small planet?" K2 to 18b doesn't contradict religious teaching. It expands our understanding of creation's magnificence. But theological interpretations varied widely. Some traditions found validation in ancient texts that spoke of life throughout the heavens. Others struggled to reconcile doctrines centered on Earth and human uniqueness with evidence of intelligence elsewhere. Interfaith dialogues about K2-18b's implications became surprisingly productive, forcing different traditions to articulate their core beliefs in new contexts. Dr. Paul Davies, physicist and astrobiologist, proposed that K2-18b's communication represented the most important discovery in human history. We've always wondered about life's nature, consciousness's origin, intelligence's development. K2-18b provides our first external reference point. We can now study intelligence that evolved independently, under different conditions, following different paths. This will revolutionize our understanding of mind, consciousness, and cognition. The discovery accelerated several scientific and technological programs. Space agencies announced enhanced plans for next-generation telescopes specifically designed to study K2-18b and similar worlds in greater detail. The proposed LAVOIR and HABEX missions gained renewed political support, with advocates arguing that understanding K2-18b should be a civilizational priority. Dr. Sarah Seeger outlined the scientific roadmap forward. We need higher resolution observations to study atmospheric structures in greater detail. Continuous monitoring to track pattern evolution in real time. Multi-wavelength observations to detect any electromagnetic emissions. And eventually, multiple independent confirmations that what we're seeing truly represents intelligence rather than unknown natural processes. The search for other examples of atmospheric engineering expanded dramatically. Astronomers began re-examining data from thousands of known exoplanets, looking for similar signatures of potential intelligence. The Breakthrough Listen project allocated substantial resources to monitoring K2-18b for radio or optical signals. SETI underwent renaissance with renewed funding and public interest. But beyond science, K2-18b was transforming human culture and philosophy. Artists created works inspired by the discovery. Musicians composed pieces imagining K2-18b's perspective. Writers explored themes of cosmic communication and civilization mortality. The discovery became cultural touchstone, reference point for discussing humanity's place in the universe. Dr. Douglas Hofstadter, cognitive scientist studying consciousness and meaning, proposed that K2-18b provided concrete validation for ideas he'd explored throughout his career. Consciousness isn't special to Earth. Intelligence emerges as natural consequence of sufficient complexity. The patterns we create, mathematical structures, artistic expressions, technological achievements, these appear to be universal features of minds everywhere. K2-18b confirms that consciousness has cosmic significance, not just terrestrial accident. Educational systems worldwide incorporated K2-18b into curricula. Children who learned about the discovery would grow up never having known a world where humans thought they were alone. Dr. Caleb Scharf, astrobiology educator, predicted this would profoundly shape future generations' worldview. These children will think differently about Earth's importance, humanity's responsibilities, and our potential future. They'll be comfortable with cosmic perspectives that previous generations struggled to grasp. the political implications extended beyond national boundaries to questions of planetary governance. If humanity needed to craft coherent responses to K2-18b, didn't that require institutions capable of speaking for Earth as a whole? The discovery reinvigorated discussions about global cooperation and unified planetary policy. Dr. Jacques Arnoul, ethics specialist for the European Space Agency, emphasized that K2-18b forced humans to consider collective identity. We've always defined ourselves in opposition, nation against nation, culture against culture. K2-18b provides an external referent. For the first time, we might meaningfully speak of humanity not as abstraction, but as concrete identity distinguished from other forms of intelligence. The economic implications were equally profound. Private space companies announced plans for enhanced observational capabilities targeting K2-18b. Breakthrough Starshot, the program aimed at sending tiny probes to nearby stars, received renewed attention and funding as people contemplated actually reaching such worlds within human timeframes. Dr. Mae Jemison argued that K2-18b should inspire massive investment in space capabilities. This isn't just about communication anymore, she declared. It's about becoming the kind of civilization that can eventually cross interstellar distances. K2-18b shows us such civilizations exist. We should aspire to become one. The philosophical implications were perhaps most profound. Dr. Nick Bostrom's work on anthropic reasoning and observation selection effects gained new relevance. If K2-18b exists despite the apparent rarity of such detections, it suggested intelligence might be more common than we'd feared, or that we were observing during a unique window when such detection became possible. Dr. Robin Hansen's Great Filter Theory underwent reassessment. If K2-18b represented advanced civilization, it suggested the filter hadn't prevented their development. But if their communication contained warnings of crisis, perhaps the filter lay ahead for both civilizations' challenges that await any technology-developing species. The discovery forced reconsideration of Fermi's paradox. The question of why we haven't detected obvious signs of intelligence if it's common. Perhaps we had detected such signs, but only recently developed instruments sophisticated enough to recognize them. Perhaps K2-18b represented the first of many discoveries as our observational capabilities matured. Dr. Jill Tarter reflected on her career searching for signals. For decades, we looked in radio frequencies, expecting technological civilizations would broadcast that way. K2-18b shows intelligence might communicate through entirely different channels: atmospheric engineering, megastructures, methods we hadn't imagined. This opens vast new search spaces. The discovery also transformed how humanity viewed its own future trajectory. Dr. Anders Sandberg, who studied long-term civilization scenarios, noted that K2-18b provided concrete evidence that technological civilizations could persist long enough to achieve atmospheric engineering at planetary scales. One of the great uncertainties about humanity's future has been whether technological species survive their own development, he explained. K2-18b suggests they can, though their apparent challenges remind us survival isn't guaranteed. The impact on space policy was immediate and far-reaching. NASA Administrator Dr. Lisa Campbell announced a comprehensive initiative to study K2-18b as humanity's top astrobiology priority. This discovery changes everything about how we search for life and intelligence, she stated at a press conference. We're no longer asking, are we alone? We're asking, what can we learn from our cosmic neighbors? The European Space Agency, JAXA, and other international partners joined in coordinated observation campaigns. Dr. Gunther Hasinger, ESA's Director of Science, emphasized the collaborative nature required. No single nation or agency can fully study K2-18b. This demands the best capabilities from across all humanity. It's forcing us to cooperate at unprecedented levels. In laboratories around the world, researchers began reconsidering fundamental questions about consciousness and intelligence. Dr. Christoph Koch, neuroscientist studying the nature of consciousness, proposed that K2-18b offered a crucial natural experiment. We've only ever studied one example of consciousness, Earth life, and specifically human minds. K2-18b potentially represents consciousness that evolved independently. Comparing their patterns and approaches to ours will reveal what's universal about mind versus what's specific to our evolutionary history. The discovery accelerated artificial intelligence research in unexpected ways. If K2-18b's patterns represented post-biological intelligence, AI systems continuing after their biological creators, it provided both warning and roadmap. Dr. Stuart Russell, AI safety researcher, noted, "We're seeing evidence of machine intelligence that persisted far beyond its creators and continued pursuing their goals for potentially centuries. This validates concerns about ensuring AI systems remain aligned with human values even after we're gone, and shows such long-term operation is possible." Conversely, some AI researchers found hope in K2-18b's patterns. If artificial intelligence could maintain complex goals and behaviors across centuries, it suggested machine minds could be stable, purposeful, and potentially benevolent. Dr. Max Tegmark observed, K2-18b's AI, if that's what we're observing, isn't paperclipping the universe into computational substrate. It's maintaining atmospheric chemistry, possibly protecting biological life, broadcasting communication. This suggests intelligence, whether biological or artificial, tends toward behaviors that preserve and create rather than destroy. The discovery's impact on environmental movements was equally profound. Dr. Jane Goodall, addressing a climate conference shortly after the K2-18b findings were announced, drew powerful parallels. We're watching another world struggle with atmospheric management. Their sophisticated technology hasn't made them immune to planetary-scale environmental challenges. This should be a wake-up call. Even civilizations far more advanced than us must actively maintain planetary habitability. We can't take Earth's stability for granted. Climate scientists found K2-18b's atmospheric engineering both inspiring and cautioning. Dr. Kate Marvel noted, "They're showing us that active climate management is possible, but also necessary. They're investing enormous resources in atmospheric maintenance. Perhaps that's the price of technological civilization. You break the natural balances, and then you must forever maintain artificial equilibrium." It's a sobering thought. The younger generation, who would inherit humanity's relationship with K2-18b, responded with particular passion. Student movements emerged advocating for educational reform, emphasizing cosmic citizenship. "We're the generation that will grow up knowing others exist," declared Maria Santos, a high school student who became spokesperson for youth perspectives on the discovery. "We need education that prepares us not just for life on Earth, but for existence in a universe with other minds." Artists and philosophers found in K2-18b endless inspiration. The atmospheric patterns inspired new forms of art. Composers translating the geometric configurations into music, visual artists creating works based on the chemical signatures, poets contemplating communication across cosmic distances. The discovery sparked what some called a cosmic renaissance, flowering of creativity, centered on humanity's new understanding of its place in the universe. Dr. Rebecca Neuberger Goldstein, philosopher studying meaning and purpose, argued that K2-18b resolved ancient philosophical questions while raising new ones. "Plato wondered if mathematical truths were discoveries or inventions," she explained. K2-18b suggests discoveries. They found the same mathematics we did, but they invented different ways to express it. The question of universals versus particulars takes on new meaning when we can compare independent civilizations. The discovery also affected how humans thought about time and legacy. Dr. David Christian, historian who studied big history and long-term perspectives, noted that K2-18b forced reconsideration of meaningful timescales. We're communicating across centuries. Any relationship with K2-18b will outlast nations, possibly outlast current religions and ideologies. We must think in terms of what endures across such spans: fundamental values, scientific knowledge, artistic expression that transcends temporary cultural particulars. Financial markets initially reacted with volatility to the K2-18b announcement, but eventually stabilized as analysts assessed implications. Dr. Catherine Wood, economist studying technological disruption, noted that space-related industries saw massive investment surges. K2-18b made space real for mainstream investors, she observed. It's not just governments exploring anymore, it's potentially the most important commercial and scientific opportunity in human history. The insurance industry faced unprecedented questions about how to assess risks in a universe with confirmed intelligence. Dr. Samuel Greengard, studying technology risk assessment, noted, "Companies are asking us to evaluate everything from brand impact of potential future contact to existential risks from advanced civilizations. We're developing entirely new frameworks for thinking about cosmic-scale uncertainties." Legal scholars grappled with questions of rights and representation. Who owned humanity's response to K2-18b? Who could claim authority to negotiate on Earth's behalf? Professor Martha Mino, studying international law and human rights, noted, "We're creating precedents that will govern humanity's cosmic relationships for centuries. The legal frameworks we establish now will shape how Earth engages with K2-18b and potentially other civilizations we discover." The military implications were carefully examined, but ultimately deemed minimal. General Laura Richardson, addressing security concerns, noted, "K2-18b is 120 light-years away. Even if they had hostile intent, the distances involved make any conflict essentially impossible with known physics. The main security consideration is ensuring humanity speaks with coordinated voice rather than competing messages that might confuse or concern them." Intelligence agencies, however, took quiet interest in K2-18b's communication methods. If atmospheric modulation could convey complex information across interstellar distances, might similar techniques work for terrestrial communication? The implications for cryptography and information security were carefully studied in classified programs. Meanwhile, ordinary people worldwide absorbed the discovery in deeply personal ways. Surveys showed that awareness of K2-18b increased feelings of cosmic connection and reduced tribalistic thinking. Dr. Elizabeth Phelps, neuroscientist studying fear and social cognition, found that K2-18b created what she called cosmic in-group expansion. People began identifying with humanity as a whole rather than narrower tribal categories. Religious attendance showed interesting patterns. Some traditions saw declines as people questioned Earth-centric doctrines, while others saw increases as people sought meaning and community in response to the discovery. Interfaith dialogue flourished as different traditions found common ground in contemplating humanity's cosmic significance. The discovery inspired new forms of ritual and meaning-making. Stargazing ceremonies became popular events where people gathered to observe in the direction of K2-18b, sharing thoughts about connection and cosmic community. Dr. Sarah Pike, studying contemporary religious movements, documented emergence of new spiritual practices centered on cosmic consciousness and interstellar communication. Mental health professionals reported mixed impacts. Some individuals experienced existential anxiety, feeling overwhelmed by the scale of cosmic distances and time. But most people reported positive psychological effects, feeling less alone, more connected to something larger, more motivated to address terrestrial problems, knowing humanity was part of a broader cosmic community. Dr. Viktor Frankl's work on meaning and purpose gained renewed attention. His argument that humans need meaning beyond mere survival resonated in context of K2-18b. If even advanced civilizations devoted resources to communication and connection, perhaps the search for meaning was indeed universal to consciousness. The K2-18b discovery also transformed how humans thought about preservation and heritage. If we were communicating with intelligence across centuries, what should we preserve? What knowledge, art, and values deserved protection for potential sharing with cosmic neighbors? UNESCO launched initiatives to identify cosmic heritage, aspects of human culture and achievement that might be meaningful to other civilizations. This forced productive debates about what truly mattered in human experience, what we wanted to represent us to the universe. Dr. Steven Pinker, studying long-term human progress, argued that K2-18b vindicated optimistic views of intelligence. Consciousness isn't an accident. It emerges, develops technology, seeks understanding and connection. Despite challenges, K2-18b persists in sophisticated communication efforts. This suggests intelligence, once emerged, has drive toward knowledge and connection that transcends immediate survival concerns. As humanity processed the discovery's implications, consensus emerged on several points. We are not alone. Even if final confirmation remained pending, K2-18b had shifted the probability of extraterrestrial intelligence from speculation to near certainty. Intelligence is purposeful. The pattern showed goal-directed behavior, sophisticated planning, and long-term commitment, suggesting consciousness naturally tends toward meaning-making and communication. Technology is powerful, but not sufficient. K2-18b's advanced capabilities didn't prevent them from facing serious challenges, suggesting even highly developed civilizations must actively manage their relationship with their environment. Communication matters. K2-18b devoted enormous resources to making themselves visible and understandable to potential observers, suggesting connection with other minds held deep value. Time requires new perspective. Communicating across centuries demanded thinking beyond individual lifespans or single generations, requiring commitment to projects whose outcomes would only be seen by distant descendants. Dr. Carl Sagan's famous phrase, "We are a way for the cosmos to know itself," took on new meaning. K2-18b suggested the cosmos knew itself in multiple ways, through different forms of consciousness emerging throughout the universe. Humanity represented one such awakening, but not the only one, perhaps not even the most advanced. As you drift toward sleep tonight, consider what K2-18b means for your own existence. You live in a moment of profound transition, after humanity's lonely childhood, but before we fully understand our place in the cosmic community. The messages traveling between Earth and K2-18b right now, crossing the vast darkness at light speed, carry the hopes and questions of minds, separated by unimaginable distance yet connected by the universal drive toward understanding. Whatever K2-18b's ultimate nature, thriving, civilization or warning from the past, biological intelligence or its artificial descendants, message of hope or cautionary tale. They've given humanity an extraordinary gift. The knowledge that consciousness is not alone, that the universe contains other minds looking outward as we do, seeking connection across the cosmic void. And perhaps most importantly, K2-18b reminds us that existence is precious, consciousness is remarkable, and the opportunity to witness and participate in the universe's awakening to itself is privilege beyond measure. Whether their story ends in triumph or tragedy, they chose to make it known, to broadcast their existence so others might learn, might feel less alone, might understand that the vast universe contains more wonders than any single world could imagine. So rest now, knowing that somewhere far away, under different skies and conditions beyond our daily experience, something exists that shares our curiosity, our drive to understand, Our hope that others like us might be watching the stars and wondering if anyone is out there looking back. Sweet dreams, cosmic citizen. You live in remarkable times. If this journey through one of the most profound discoveries in human history has moved you, inspired you, or left you wanting to learn more about our place in the cosmos, please subscribe to our channel. Hit that bell icon to be notified when we explore more mysteries at the intersection of cutting-edge science and cosmic wonder. Share this documentary with others who find meaning in understanding our universe, and leave a comment telling us, how does knowing about K2-18b change how you see your own life and humanity's future? The conversation between Earth and K2-18b will continue for centuries. Subscribe to be part of humanity's ongoing journey of cosmic discovery. Thank you for watching, for wondering, and for being part of this extraordinary moment in our species' story.